Have you ever looked up at the night sky and felt that sense of wonder, that quiet awe at the vastness of the cosmos? We've been gazing at the stars for thousands of years, mapping constellations, tracking planets, and building telescopes powerful enough to see billions of light years into the past. Yet, for all our knowledge and all our technology, we've only been seeing a fraction of the true picture. In fact, everything we've ever observed with our eyes or instruments, every star, every galaxy, every swirling nebula makes up just 5% of the universe. The rest is an enigma, a cosmic secret hiding in plain sight. This is where the story takes a breathtaking turn. The universe, it turns out, is like an iceberg floating in an endless dark sea. We've been marveling at the tip, the glittering, visible part, while beneath the surface lies something far larger, stranger, and more mysterious. That hidden 95% is composed of two profound and elusive forces, dark matter and dark energy. They don't emit light, they don't reflect it, and they don't interact with ordinary matter in any way we can directly detect. They are, by every definition, invisible. And yet, without them, galaxies would fly apart, the cosmos wouldn't have formed the way it did, and the universe as we know it simply wouldn't exist. What you're about to experience is a journey into the heart of that mystery. We'll explore how scientists first stumbled upon these cosmic ghosts, what clues they've gathered, and why after decades of searching, we still haven't found the answers. This isn't just a story about astronomy or physics. It's about human curiosity itself, our relentless drive to understand the unknown, even when it remains just out of reach. So settle in. Over the course of this video, we'll unravel the science, the history, and the enduring questions behind two of the greatest puzzles the universe has ever presented. You're about to see the cosmos in a whole new light. Our journey into this cosmic mystery begins not with a sprawling space telescope or a billion-dollar particle accelerator, but with a brilliant and often cantankerous astronomer named Fritz Zwicky, working at the California Institute of Technology in the 1930s. Zwicky was studying a huge group of galaxies known as the Coma Cluster, a distant metropolis of stars millions of light-years away. He was measuring how fast these individual galaxies were orbiting the cluster's center, and what he found was deeply unsettling. According to the well-established laws of gravity, the speed of those galaxies was a direct clue to the cluster's total mass. The faster they moved, the more mass and therefore the more gravity was needed to keep them from flying off into the void. But when Zwicky added up all the mass, he could see every single star, every wisp of gas and cloud of dust within those galaxies. It was nowhere near enough to account for their tremendous velocity. The galaxies were moving so fast that the visible matter provided only a tiny fraction of the gravitational glue required to hold the entire cluster together. The rest was simply missing. Zwicky, with his characteristic flair, dubbed this invisible material Dunkel Materie, or dark matter. It was a monumental claim, and for decades it was largely dismissed by the scientific community as an anomaly, a miscalculation, or the work of an eccentric mind. The case for this missing mass might have ended there, gathering dust in old astronomy journals, if not for the meticulous work of another groundbreaking astronomer decades later. In the 1970s, Vera Rubin and her colleague Kent Ford were studying individual galaxies, not clusters. They were meticulously mapping the rotation curves of spiral galaxies, essentially, charting how fast stars orbited the galactic center at different distances. According to Newtonian physics, stars on the outer edges of a galaxy, far from the central bulge of mass, should orbit much more slowly, just as Pluto, at the edge of our solar system, moves far more sluggishly around the Sun than Mercury does. But Rubin's data revealed something astonishing and uniform. No matter how far out a star was, its orbital speed remained almost constant. The rotation curves were flat. This was a direct violation of expectations. It meant that the gravitational force holding these distant stars in their speedy orbits wasn't coming from the bright, visible center of the galaxy. Instead, it implied that each galaxy was enveloped in a massive, invisible sphere of something, a halo of matter that extended far beyond the reach of its luminous stars. This something was exerting a gravitational pull, providing the extra glue that the equations demanded. Rubin had not only confirmed Zwicky's old hypothesis, but had shown that this wasn't just a problem for giant clusters. It was a fundamental feature of every single galaxy we could observe. So if the gravity wasn't coming from the stars and gas we could see, where was it coming from? Vera Rubin's work pointed overwhelmingly to an invisible source, but the evidence was still indirect, a story told through the speed of stars. To truly convince the scientific community, astronomers needed to find a way to actually picture this invisible stuff. And remarkably, they found a way to do exactly that by using the universe itself as a giant lens, thanks to a prediction made by Albert Einstein himself. Einstein's theory of general relativity proposed that massive objects don't just create a gravitational pull, they actually warp the very fabric of space-time around them. Think of space as a taut rubber sheet. Place a heavy bowling ball in the center and it creates a deep dip. Now roll a marble past it. Its straight path will bend as it curves around the depression. In the same way, a massive object like a galaxy cluster bends the space around it, and this curvature deflects the path of light traveling from more distant galaxies behind it. From our viewpoint, this creates a spectacular cosmic illusion. The background galaxy can appear stretched, magnified, or twisted into multiple images, like looking through a giant funhouse mirror in space. This phenomenon is called gravitational lensing, and it gives astronomers a direct tool to map the total mass of the foreground cluster, because the amount of bending directly correlates to the amount of mass causing the warp. For most clusters, the lensing effect creates graceful, faint arcs of light, the smeared images of those background galaxies. And for a long time, that's exactly what scientists observed. But then they started finding clusters where the story told by the light was completely at odds with the story told by the gravity. The most famous and compelling example of this is the Bullet cluster. This isn't a single serene galaxy cluster, but actually two massive clusters that have recently collided and passed right through one another. This cosmic crash was a perfect natural experiment. During such a collision, the different components of the clusters behave in very different ways. The clouds of hot, glowing gas that make up the majority of the visible mass are like two clouds of smoke. When they collide, they slam into each other, creating immense friction and shock waves that slow them down dramatically. This gas becomes separated from the galaxies themselves. But when astronomers mapped the Bullet cluster, they found something astounding. Using telescopes that see X-rays, they could pinpoint where the majority of the visible mass that slowed down gas was located. Then, by meticulously measuring the gravitational lensing effect, they mapped the true distribution of the cluster's total mass, the source of the gravity that was bending the light. The two maps did not match at all. The peak of the gravitational mass wasn't centered on the gas clouds where the visible matter was concentrated. Instead, the gravitational centers were aligned almost perfectly with the locations of the galaxies themselves, which had sailed right through the collision relatively unscathed, much like a swarm of bees would fly through a cloud of smoke. This was a direct visualization of dark matter. The collision had effectively stripped the visible matter away from the invisible matter, revealing that the majority of the mass, the stuff creating the gravitational lensing effect, was completely dark. It didn't emit light, it didn't interact with the gas, it just kept on going, governed by gravity alone. Here was a situation where we could literally see the separation between what is visible and what exerts the dominant gravitational force, providing some of the most tangible and convincing evidence that dark matter is not only real, but it is a distinct physical substance that permeates our universe. So we have this compelling, almost ghostly evidence for dark matter's existence from the way it bends light and guides galaxies. But this leads to an even more profound question. Just how much of this mysterious stuff is actually out there? Is it a minor component, or does it dominate the cosmos? For decades, these were open questions debated among cosmologists. The answer, it turns out, was imprinted on the sky at the very dawn of time, and it took a space-based observatory of incredible sensitivity to finally read it. To understand this, we need to travel back not just millions, but nearly 14 billion years to the origin of the universe itself. In the first hot, dense moments after the Big Bang, the entire cosmos was a searing, opaque plasma, a thick soup of particles and energy where light was constantly trapped, bouncing off free electrons. It was a chaotic, blinding fog. Then, about 380,000 years later, something monumental happened. The universe had expanded and cooled just enough for electrons to combine with protons, forming the first neutral atoms. In that instant, the fog suddenly lifted. The light, which had been trapped for eons, was finally set free to travel across the universe. That first burst of light, now stretched and cooled by the immense expansion of space over billions of years, still fills the entire cosmos. We detect it today as a faint, cold microwave glow coming from every direction, a relic from the infancy of everything. This is the cosmic microwave background, and it is the single most important baby picture of our universe ever taken. But it's not a perfectly smooth, uniform picture. If you look closely, you'll see it's mottled with tiny variations, minute differences in temperature, tiny patches that are ever so slightly warmer or colder than the average. These fluctuations are not random noise. They are a frozen record of sound waves echoing through the early plasma. Think of the early universe as a ringing bell. Dense regions pulled by gravity would collapse inward, but the intense radiation pressure inside would push back out, creating a rhythmic oscillation, a booming echo of compression and rarefaction. These are Barrian acoustic oscillations. When the universe became transparent, that ringing stopped instantly, freezing these waves in place and imprinting their pattern onto the light of the CMB. The specific pattern of these hot and cold spots, their size and distribution, is a cosmic fingerprint. It tells us everything about what the universe is made of, because each component of the cosmos, ordinary matter, dark matter, and dark energy, affects these sound waves in a unique way. Ordinary matter, with its ability to interact with light and radiation, has a certain gravitational pull. Dark matter, which only feels gravity, provides the main gravitational anchor for these waves but doesn't interact with the radiation pressure. And dark energy, as we'll see, influences the overall expansion rate. The size of the most common waves we see in the CMB, the preferred scale of these oscillations, acts like a standard ruler. By measuring this ruler with exquisite precision, we can work backwards to calculate the exact recipe of the universe. This is where the European Space Agency's Planck satellite comes in. Launched in 2009, Planck was designed to be the ultimate cartographer of this ancient light. It spent over 4 years staring into the depths of space, measuring the temperature of the CMB with a sensitivity so incredible it could detect variations of a millionth of a degree. What it found was the most detailed map of the early universe ever created, a map so precise it could measure the fundamental ingredients of the cosmos to within a single percent. The results were nothing short of definitive. Planck's measurement of those acoustic peaks revealed that ordinary matter, the atoms that make up stars, planets, and us, constitutes a mere 4.9% of the universe. The dark matter, whose gravitational signature we see in galaxies and clusters, makes up 26.8%, and the remainder, a staggering 68.3%, is the even more mysterious dark energy. The universe, in its very first whisper, told us its exact composition. It confirmed that the stuff we know and understand is the rarest component of all, and that the true cosmic landscape is dominated by two profound and invisible mysteries. With the universe's recipe now clearly defined by the cosmic microwave background, a new and equally profound question emerges. If ordinary matter makes up less than 5% of the cosmos, how did it ever manage to clump together to form the magnificent structures we see today, the glittering spiral galaxies, the massive elliptical galaxies, and the immense clusters that dot the cosmos? The answer lies not with the atoms themselves, but with the unseen scaffolding provided by dark matter. In the early universe, dark matter held a crucial advantage. Because it doesn't interact with light or radiation, it was immune to the intense pressure that filled the cosmos in its first few 100,000 years. While ordinary matter, a superheated plasma of protons and electrons, was buffeted by powerful photons, preventing it from collapsing under its own gravity, dark matter was free to begin coalescing. It started to gather into vast, invisible clouds, drawing itself together through its own gravitational pull. These nascent clouds, known as dark matter halos, became the gravitational anchors, the foundational skeletons upon which everything visible would later be built. This process is known as the hierarchical model of structure formation. It begins with the tiny fluctuations imprinted in the CMB, those faint ripples from the universe's infancy. The slightly denser regions within the dark matter began to pull in more and more dark matter from their surroundings. Over hundreds of millions of years, these small halos grew larger, not just by gently accumulating material, but often through dramatic mergers and acquisitions. Smaller halos would be drawn into the gravitational well of larger ones, colliding and combining to build ever more massive structures. This created a vast cosmic web, an intricate network of dark matter filaments connecting dense nodes where immense halos resided. And it was within the deep gravitational wells of these halos that the fate of ordinary matter was decided. The hydrogen and helium gas that filled the early universe, once it had cooled and become neutral after the release of the CMB, began to feel the irresistible pull of these dark matter concentrations. Drawn in by the powerful gravity of the invisible halo, vast rivers of gas flowed along the dark matter filaments, channeling themselves into the centers of these potential wells. As the gas fell inward, it compressed, heated up, and eventually began to cool again by radiating away its energy. This cooling was the critical final step. It allowed the dense clouds of gas to collapse further, fragmenting into the first generation of stars. These first stars then lit up within the heart of the dark matter halo, birthing the very first proto-galaxies. Without the dark matter halo to first gather and hold onto this gas, it would have simply drifted apart. The gravity from the paltry amount of visible matter alone was far too weak to overcome the gas's own kinetic energy and thermal pressure. This explains why the dark matter halo is so essential, and why its properties directly dictate the properties of the galaxy that forms inside it. The size and mass of the halo determines how much gas it can pull in. A massive halo might eventually host a giant elliptical galaxy, while a smaller one could become the home of a dwarf or a spiral galaxy like our own Milky Way. In fact, our galaxy is embedded within a huge, roughly spherical halo of dark matter that extends far beyond the visible edge of its spiral disk. This framework elegantly solves the mystery of those flat rotation curves observed by Vera Rubin. The stars on the outer edges of a galaxy are orbiting rapidly because they are deep within the gravitational influence of this immense, unseen sphere of mass. Contemplating a universe without dark matter reveals just how vital it is to our existence. In such a cosmos, the initial tiny fluctuations in ordinary matter would have struggled to grow. Without the gravitational head start provided by dark matter's early collapse, the outward pressure of radiation would have washed out these small density variations. The universe would have continued to expand, but it would have remained a vast, dark, and profoundly lonely place, a nearly uniform and ever-diffusing sea of hydrogen gas. There would be no galaxies, no stars, no planets, and consequently, no life. The cosmic structures we marvel at are not just influenced by dark matter, they are fundamentally and irrevocably built by it. It is the hidden architect of the visible universe. For centuries, the central question in cosmology was a simple one: what is the ultimate fate of the universe? Given the relentless pull of gravity between all matter, scientists were certain the cosmic expansion that began with the Big Bang must be slowing down. The only real debate was over the details. Would the deceleration be enough for gravity to eventually halt the expansion and pull everything back in a catastrophic big crunch? Or would the universe simply coast forever, expanding at a slower and slower rate towards a cold, quiet fade out? Every major theory pointed to one of these two outcomes: a universe steadily slowing down under its own weight. This fundamental assumption was so deeply ingrained that when two rival teams of astronomers set out in the 1990s to measure this deceleration with exquisite precision, they fully expected to simply determine which gloomy ending awaited us. They were about to make one of the most startling discoveries in the history of science. These teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were using the same powerful tool to conduct their cosmic census: Type 1, a supernova. These spectacular stellar explosions are the perfect standard candles for measuring vast intergalactic distances. A Type 1, a supernova, occurs in a binary star system where a dense white dwarf siphons material from its companion. Once it reaches a very specific critical mass, it undergoes a runaway thermonuclear explosion. Because this critical mass is always the same, the intrinsic brightness of the explosion is also always the same. This means that by measuring how bright or faint the supernova appears from Earth, astronomers can calculate its exact distance with remarkable accuracy. Furthermore, by analyzing the redshift of the light from the supernova's host galaxy, they can determine how much the universe has stretched since the moment the star exploded. The plan was straightforward. By looking back in time at supernova billions of light years away, the teams could effectively measure the expansion rate of the universe at different epochs in its history. They would compare the expansion rate in the distant past to the rate today. If the universe was slowing down as expected, the very distant, ancient supernova should appear brighter than their redshift would suggest. Why? Because in a decelerating universe, the expansion was faster in the past, meaning those ancient supernovae would be physically closer to us than they would be in a universe that expanded at a constant rate. Their light wouldn't have had to travel as far through an ever-slowing expansion, so they would seem abnormally bright for their redshift. After years of painstaking observation, collecting data from the most powerful telescopes on Earth and in space, both teams made the same baffling discovery. The distant supernovae were not brighter than expected, they were significantly fainter. This was the complete opposite of what every model had predicted. A faint supernova meant it was much farther away than anyone had calculated. For the light from these incredibly distant explosions to have reached us, the universe must have been expanding more slowly in the past. The expansion, against all logic and against the relentless pull of gravity, was not slowing down. It was speeding up. Something was actively forcing galaxies to fly apart from one another at an ever-increasing rate. The two teams, initially in a fierce competition, found themselves independently arriving at the same unbelievable conclusion. They were so stunned by their own results that they spent months checking and rechecking for errors, searching for any possible mundane explanation, dust obscuring the light, evolutionary changes in the supernova, anything. But the data was robust and the conclusion was inescapable. In 1998, they announced their findings to a shocked world, a discovery that would eventually earn them the Nobel Prize in Physics. This revelation introduced a monumental new mystery into the heart of cosmology. What could possibly be causing this cosmic acceleration? Gravity only pulls things together, it never pushes them apart. The only force that could counter gravity's attractive grip on such a colossal scale would be a form of anti-gravity, a pervasive repulsive force embedded within the fabric of space itself. This mysterious something was dubbed dark energy. The Planck satellite's later measurements of the cosmic microwave background would confirm its overwhelming dominance, showing that dark energy constitutes about 68% of the entire universe. But its nature remains one of the greatest enigmas in physics. The most straightforward explanation, though it leads to profoundly strange implications, is the cosmological constant, an energy inherent to the vacuum of empty space. This idea was first proposed and later rejected by Einstein himself as his greatest blunder. According to quantum physics, empty space is not truly empty but seethes with virtual particles constantly flickering in and out of existence. This quantum foam could possess a repulsive energy that causes space itself to expand. The problem is that when physicists try to calculate the strength of this vacuum energy using our current theories, the predicted value is staggering, up to 120 orders of magnitude too large. If that were true, the universe would have been torn apart in its first instant of existence. This colossal mismatch between theory and observation is a clear signal that our understanding of fundamental physics is profoundly incomplete. So if dark energy is this repulsive force accelerating the expansion of the cosmos, the most elegant explanation is one that was born from a moment of frustration nearly a century ago. It brings us back to Albert Einstein and his theory of general relativity. When Einstein applied his beautiful equations to the universe as a whole, he encountered a problem. The equations described a dynamic universe, one that should naturally be either expanding or contracting under gravity's influence. But this was the early 20th century, and the prevailing scientific view shared by Einstein was of a static, eternal, and unchanging universe. To reconcile his theory with this belief, he introduced a fudge factor, a term represented by the Greek letter lambda. This cosmological constant was a repulsive force that would perfectly balance the attractive pull of gravity on the largest scales, creating a static, stable cosmos. It was a mathematical placeholder for energy inherent to the vacuum of space itself. Years later, when Edwin Hubble's observations proved the universe was indeed expanding, Einstein famously discarded the cosmological constant, calling it his greatest blunder. He saw it as an unnecessary complication, a mistake that had prevented him from predicting the expansion of the universe. The idea was largely shelved for decades. But the discovery of the accelerating universe in the late 1990s brought lambda back from the dead with a vengeance. Suddenly, cosmologists needed exactly that kind of repulsive energy to explain what was happening. In this modern context, the cosmological constant is imagined as the energy density of empty space itself. According to quantum physics, a vacuum is not truly empty. At the tiniest scales, it is a seething, bubbling foam of virtual particles. These particle-antiparticle pairs constantly flicker into and out of existence, borrowing energy from the vacuum for an incredibly brief moment before annihilating and returning it. This bizarre but well-established quantum behavior should endow every cubic centimeter of empty space with a certain amount of energy, and this vacuum energy would have a repulsive gravitational effect, exactly the property needed to explain dark energy. It was a beautiful marriage of quantum mechanics and cosmology. The ghost of Einstein's blunder seemed to have provided the perfect answer. The triumph, however, was devastatingly short-lived. When physicists sat down to actually calculate the expected value of this vacuum energy, the result was so catastrophically wrong it became known as the worst theoretical prediction in the history of science. The calculation involves summing up all the contributions from every possible quantum field fluctuation, but the result is a number that is unimaginably large. The predicted energy density of the vacuum is around 120 orders of magnitude. That's a 1 followed by 120 zeros greater than the value we actually observe from the acceleration of the universe. To put that incomprehensible error into perspective, It's the difference between the energy stored in a single gallon of gasoline and the energy of the entire observable universe. If the quantum field calculation were even remotely correct, the repulsive force of this vacuum energy would have been so immense that it would have ripped every atom apart instantaneously after the Big Bang. Galaxies, stars, and life could never have formed. The universe as we know it would not exist. This staggering discrepancy is more than just a simple miscalculation. It is a fundamental crisis in physics. It tells us with absolute certainty that our two most successful and powerful theories, quantum mechanics, which governs the very small, and general relativity, which describes the very large, are fundamentally incompatible on this point. We are missing a deep piece of the puzzle. Some physicists hope that a future theory of quantum gravity, like string theory, might provide a mechanism that cancels out almost all of this vacuum energy, leaving behind the tiny, residual amount we see as dark energy. Others propose that the cosmological constant isn't truly constant at all, but a dynamic field that has evolved over time, an idea known as quintessence. Or perhaps our understanding of gravity itself is incomplete on the largest scales, requiring a modification to Einstein's equations. The cosmological constant offers an elegant explanation for dark energy, but it simultaneously exposes a profound gap in our understanding of reality, a mystery that stretches from the quantum foam to the cosmic horizon. While the evidence for dark matter's gravitational influence is overwhelming, its elusive nature has led some scientists to question the underlying assumption itself. What if we're not missing a type of matter, but instead our understanding of gravity is incomplete? This is the provocative premise behind the most prominent alternative to dark matter, modified Newtonian dynamics, or MND. Proposed by physicist Mordechai Milgrom in the early 1980s, MND suggests that gravity doesn't behave exactly as Newton or Einstein described in the extremely weak gravitational fields found at the outer edges of galaxies. Instead of needing extra invisible mass to explain why stars orbit so quickly, MND proposes a simple modification to the laws of motion. It suggests that below a certain very low acceleration threshold, gravity becomes stronger than the traditional inverse square law predicts. This tiny tweak to the formula was remarkably successful. Without invoking a single particle of dark matter, MND could accurately reproduce the flat rotation curves of spiral galaxies that had baffled astronomers. It wasn't just a fit for one galaxy, it became a predictive framework. For many proponents, this was an elegant solution that adhered to a principle of scientific parsimony, often called Occam's razor, which favors simpler explanations without inventing new, undetected substances. The appeal of MND and its refinements lies in its ability to solve specific galactic puzzles with stunning precision. For certain types of galaxies, particularly low-surface brightness galaxies where the discrepancy between visible mass and gravitational pull is most pronounced, MND predictions match the observed rotation curves almost perfectly. These successes aren't easily dismissed and highlight why the theory has persisted as a compelling counter-narrative for decades. It forces the mainstream scientific community to continually test and verify the dark matter paradigm, strengthening the overall investigative process. However, for a theory to truly replace the standard model of cosmology, it must explain all the evidence, not just a compelling subset. This is where MND and other modified gravity theories encounter their greatest challenges. The first major hurdle appears when we zoom out from individual galaxies to the scale of immense galaxy clusters. Remember the bullet cluster? That cosmic collision provided a direct visual map separating the visible matter from the source of gravity. MND, which modifies the force of gravity itself, struggles to explain this result because the gravity is clearly not centered on the visible mass. The gravitational lensing map shows the mass is in a different location, which is a natural outcome for dark matter but a serious problem for a modified gravity model. Furthermore, the observed motions of galaxies within clusters and the temperature of the hot gas trapped there require far more mass than MUND can account for with its modified equations. To explain these large-scale phenomena, even the most ardent MUND supporters have had to concede that some form of additional, unseen matter is still needed, neutrinos or other known particles, effectively making it a hybrid model rather than a clean alternative. But the most definitive evidence against a pure modified gravity approach comes from that same ancient light that gave us the universe's recipe, the cosmic microwave background. The precise pattern of fluctuations in the CMB is a detailed record of how gravity, dark matter, and radiation interacted in the early universe. Computer simulations of the universe's evolution show that a model with dark matter produces acoustic oscillations that match the Planck satellite's map with incredible accuracy. When scientists run simulations using only modified gravity like MUND without dark matter, the resulting pattern looks nothing like the universe we actually observe. The peaks and troughs in the temperature variations are in all the wrong places. The sound waves don't propagate correctly because the gravitational anchoring so crucial for forming the first structures is absent. The CMB data is perhaps the most powerful argument for the existence of a collisionless, cold dark matter component that existed long before galaxies ever formed. The ongoing tension between these models is a fascinating and healthy part of the scientific process. It pushes researchers on both sides to refine their ideas and search for more conclusive evidence. Modern iterations of modified gravity, such as tensor vector scalar gravity, attempt to reconcile these issues by building more complex frameworks, but they often lose the elegant simplicity that made original MUND so attractive. The core of the debate ultimately circles back to a fundamental choice. Do we accept that the universe is predominantly made of a mysterious, invisible substance that has so far evaded all our attempts at direct detection? Or do we rewrite our understanding of one of the most fundamental forces in nature? For the vast majority of cosmologists, the collective weight of evidence from clusters, the CMB, and large-scale structure points overwhelmingly toward the existence of dark matter. Yet, the persistence of modified gravity theories serves as a crucial reminder that in our quest to understand the cosmos, we must always be willing to question our most basic assumptions. So if the majority of matter in the universe is this invisible, gravity-producing substance, what exactly is it made of? For decades, physicists have been hunting for the answer, and their search has centered on one particularly compelling idea. That dark matter consists of entirely new, undiscovered particles that don't interact through the electromagnetic force, making them effectively transparent. The leading candidate for this role has been a hypothetical class of particles known as WIMP, or weakly interacting massive particles. The appeal of the WIMP is rooted in a beautiful, albeit unproven, concept known as the WIMP miracle. The theory suggests that in the incredibly hot, dense conditions just after the Big Bang, these particles would have been created in abundance. As the universe expanded and cooled, they would have annihilated each other upon collision, but the expansion would have eventually diluted them to the point where they could no longer find each other to annihilate. The remaining relic density, the leftover population of these particles, can be calculated, and astonishingly, it predicts a quantity of dark matter that aligns perfectly with the 27% of the universe we observe today. It was a stunning coincidence that suggested nature might be offering us a huge hint, making WIMP the darling of particle physics for a generation. The proposed properties of a WIMP make it a perfect fit for the cosmic role of dark matter. As the name implies, a weakly interacting massive particle would have significant mass, perhaps anywhere from tens to thousands of times the mass of a proton. More crucially, its interaction would be exclusively through gravity and the weak nuclear force, the same force responsible for radioactive decay. This weakness is its defining feature. It explains why dark matter can pass through entire planets without a trace. It simply doesn't engage with the ordinary matter that makes up our world. You are likely being streamed through by billions of these particles every second, completely unaware of their presence. This very elusiveness, however, is what makes detecting them one of the greatest experimental challenges of our time. To have any hope of catching a WIMP, scientists realized they needed to go to extreme lengths to eliminate all background noise. They built incredibly sensitive detectors and placed them deep underground in abandoned mines or beneath mountains. The rock overhead acts as a colossal filter, shielding the experiments from the constant barrage of cosmic rays that would otherwise overwhelm any faint signal. Within these pristine, silent laboratories, detectors are cooled to temperatures near absolute zero. They contain large vats of ultra-pure materials like liquid xenon or germanium crystals, which serve as the target. The concept is breathtakingly simple in theory. Wait for a WIMP from the galactic halo to very rarely bump into the nucleus of an atom in this target. That tiny transfer of energy, that minuscule recoil, would generate a faint flash of light or a release of charge that the exquisitely sensitive instruments could, in principle, detect. For over 30 years, these experiments have been running, growing larger, more sensitive, and more sophisticated with each iteration. They have painstakingly charted the background interactions from known sources like neutrons, pushing the boundaries of what can be detected into realms of incredible sensitivity. And yet, despite this monumental effort, the result has been a profound and growing silence. Not a single confirmed, unambiguous WIMP signal has ever been recorded. The experiments have excluded vast swaths of the possible mass and interaction strengths where these particles could have been hiding. Each new, more powerful detector was built with the hope that it would be the one to make the historic discovery, only to further narrow the search window. This decades-long null result has forced a major re-evaluation within the physics community. The WIMP miracle now feels less like a divine hint and more like a beautiful idea that nature might simply have passed by. It doesn't mean WIMP are entirely ruled out. They could still exist in regions of parameter space that are even more difficult to probe, interacting so weakly that our current technology is still not sensitive enough. But the initial optimism has certainly given way to a more sober and broad-minded approach, encouraging physicists to look beyond the WIMP paradigm for answers to the dark matter question. With a persistent silence from WIMP detectors casting a long shadow, the search for dark matter's true identity has dramatically broadened. Physicists are now venturing into far more exotic territory, exploring a menagerie of alternative candidates that would have seemed like science fiction just a few decades ago. Leading this new charge is a particle with a fascinating origin story, one born not from cosmology but from the perplexing puzzles of the subatomic world, the action. The action was first proposed in the 1970s by physicists Roberto Pexi and Helen Quinn to resolve a glaring inconsistency in the strong nuclear force, the force that holds atomic nuclei together. The theory of quantum chromodynamics, which describes this force, seemed to allow for violations of a fundamental symmetry known as CP conservation. In practical terms, this should have given the neutron a surprisingly large electric dipole moment, a sort of inherent spatial asymmetry. Yet, incredibly sensitive experiments have found the neutron to be perfectly symmetrical to an astonishing degree. The action was the elegant solution, a new field that would dynamically correct this imbalance and preserve the symmetry. It was a fix for particle physics, but it soon became clear that this hypothetical particle had all the right properties to be dark matter. Actions would be extraordinarily light, potentially billions of times lighter than an electron, and they would be produced in colossal numbers in the hot early universe. Most importantly, they would interact with ordinary matter only very weakly and extremely rarely, making them effectively invisible and a perfect fit for the dark matter profile. Finding something so tiny and so ghostly requires a completely different approach from the large vats of xenon used to hunt for WIMP. Action hunters use powerful magnetic fields to try and coax these elusive particles into revealing themselves. The theory suggests that in the presence of a strong magnet, an action could convert into a faint microwave photon. So, experiments consist of immense, superconducting magnets chilling massive cavities to near absolute zero, all housed in radio frequency shielded rooms. Researchers then meticulously tune these cavities, like slowly turning a dial on a cosmic radio, listening for a specific, faint whisper of frequency that would signal an action converting within the magnetic field. It's a painstaking process, a search for a needle in a haystack where you're not entirely sure what the needle looks like. While no definitive signal has been found yet, the sensitivity of these experiments is improving rapidly, and many scientists believe the action's ultra-light nature makes it an increasingly compelling candidate. Another intriguing possibility comes from a familiar particle with a mysterious twist, the neutrino. We know neutrinos exist. They're produced in the sun, in nuclear reactors, and in supernova, and they flood through the universe almost completely unimpeded. But the standard model of particle physics only accounts for three types: the electron, muon, and tau neutrinos. What if there is a fourth kind? This hypothetical particle is known as a sterile neutrino. It would interact only through gravity, not even through the weak nuclear force like its standard model cousins, making it utterly dark and undetectable by conventional means. Sterile neutrinos could have been produced in the early universe and could account for a portion, if not all, of the dark matter. Some tantalizing, though still unconfirmed, anomalies in nuclear reactor data and observations of certain X-ray emissions from distant galaxies have been put forward as potential hints of their existence, adding an extra layer of excitement to this line of inquiry. Perhaps the most dramatic alternative, however, requires no new particles at all. What if dark matter is made of ancient black holes formed not from the collapse of giant stars, but in the chaotic first second after the Big Bang? These primordial black holes would be true relics of creation. Their mass could range from something smaller than an atom to larger than a star, and because they are simply compacted gravity, they would be completely dark unless they are actively consuming material. This idea has seen a major resurgence, particularly after the LIGO Observatory began detecting gravitational waves from merging black holes whose masses were curiously in a range that is difficult to explain through standard stellar evolution. Could some of these be primordial? The challenge is that too many primordial black holes would have left observable imprints on the cosmos, such as disrupting the neat pattern of the cosmic microwave background or distorting the light from distant stars through frequent microlensing events. While they likely cannot account for all the dark matter, they remain a fascinating and plausible component of the cosmic inventory. This expanding field of candidates reflects a fundamental shift in how we approach the dark matter problem. The failure to find WIMP has not been a defeat but a liberation, forcing cosmologists and particle physicists to think more creatively than ever before. We are now testing the boundaries of known physics, from the impossibly light to the extraordinarily dense, in a grand experimental effort to identify the unseen majority of our universe. Each candidate, from the wispy action to the primordial black hole, tells a different story about the conditions of the early cosmos and the fundamental laws that govern it. The search has become a wider, deeper, and more exciting puzzle than anyone could have imagined. This relentless pursuit of the invisible has led to some of the most extreme and sophisticated scientific experiments ever conceived. To have any hope of detecting a dark matter particle, researchers had to create environments of unparalleled stillness and silence, far removed from the cacophony of the surface world. The primary challenge is cosmic rays, a constant rain of high-energy particles from space that would create a relentless barrage of false signals in any detector. The solution was to go deep underground, using the Earth itself as a shield. In abandoned gold mines in South Dakota, in tunnels under mountains in Italy, and in laboratories buried beneath miles of rock in Canada, scientists have built cathedrals to the unknown. These are the direct detection experiments, and they represent humanity's most direct attempt to reach out and touch the dark universe. Experiments like LUX, the Large Underground Xenon Experiment, and its massive successor, Lux Zeppelin or LZ, are marvels of engineering. At their heart is a concept of beautiful simplicity. Wait for the unseen to make itself known through a single, infinitesimal collision. They use large vats of ultra-pure liquid xenon, a dense and noble element chosen because its large atomic nuclei provide a bigger target for a potential dark matter particle to hit. This core detector is housed within a Russian nesting doll of protective shields tanks of ultra-pure water, layers of lead and copper, all designed to block out any trace of natural radioactivity from the surrounding rock and materials. The entire apparatus is then cooled to extreme temperatures and monitored by arrays of exquisitely sensitive light sensors. The theory is that if a WIMP or another dark matter candidate were to drift through the tank and ever so rarely bump into a xenon nucleus, the interaction would produce two telltale signals: an immediate flash of light followed by a delayed burst of electrical charge. The precise timing and ratio of these two signals would be the unmistakable fingerprint of a genuine particle event, distinguishing it from any remaining background noise. The scale of these endeavors is breathtaking. The Xenon Collaborations detector at the Gran Sasso Laboratory in Italy uses several metric tons of liquid xenon, so pure that even a single contaminant could ruin the search. The Panda X experiment in China operates under similar pristine conditions. For years, these teams have operated their detectors in a state of suspended anticipation, collecting data in runs that last for hundreds of consecutive days, all in the hope of capturing a handful of those priceless, elusive recoils. The process is one of incredible patience and precision, a testament to the dedication required to probe the farthest edges of known physics. And yet, the result from all of them, after decades of operation and continuous refinement, has been the same: a profound and telling silence. The detectors have not found a single, unambiguous signal that can be attributed to dark matter. This null result, however, is far from a failure. In science, knowing where something isn't is just as valuable as knowing where it is. Each experiment has systematically ruled out vast territories on the map of possible dark matter particles. They have placed incredibly stringent limits on how strongly these particles can interact with ordinary matter, effectively closing the door on the most promising and popular models for WIMP. This has forced theoretical physicists back to the drawing board, compelling them to consider lighter, weirder, or more weakly interacting candidates that they might have previously overlooked. The silence from deep underground is a powerful message from the universe, telling us that the answer is not where we first thought it would be, and challenging us to think even more creatively about the nature of the cosmos. Faced with the quiet from deep underground, scientists realized they needed a completely different strategy. If dark matter won't come to our detectors, perhaps we can observe it from a distance by looking for the aftermath of its own destruction. This approach, known as indirect detection, turns the entire universe into a giant laboratory. The theory is based on a fascinating possibility. While dark matter particles mostly ignore each other and everything else, there's a chance they could occasionally interact with one another. If two dark matter particles were to collide, they might annihilate each other in a flash of energy, transforming into a shower of familiar particles we can see, most notably highly energetic gamma rays. Our best chance of spotting this cosmic fireworks show isn't from a lab on Earth, but from a powerful telescope orbiting high above our planet's atmosphere. The Fermi Gamma Ray Space Telescope and its primary instrument, the Large Area Telescope, or Fermi LAT, was launched for exactly this kind of exploration. Unlike optical telescopes that see visible light, Fermi is designed to see the universe in gamma rays, the most energetic form of light. This is crucial because the annihilation of massive dark matter particles would be expected to produce gamma rays with very specific high energies. To find this elusive signal, astronomers need to point their telescope at the places where dark matter is thought to be at its most dense and abundant. Two of the most promising targets are the centers of galaxies and tiny, ancient satellite galaxies that orbit our own Milky Way. The heart of our galaxy is a compelling hunting ground. Based on the gravitational maps we have, the Milky Way center should contain an incredibly dense, concentrated blob of dark matter. If annihilation is happening anywhere, the rate should be highest there due to the sheer number of particles. However, the galactic center is also a notoriously chaotic and bright environment in gamma rays, filled with pulsars, supernova remnants, and other energetic objects that create a complex background of emission. Disentangling a potential dark matter signal from this astrophysical cacophony has proven to be incredibly difficult. Some analyses have suggested a curious excess of gamma rays at just the right energy range, but so far, it's impossible to rule out that it's just a collection of unknown, conventional point sources. This is why many researchers believe the best places to look are actually the darkest places in the sky, dwarf spheroidal galaxies. These are tiny, faint galaxies that orbit the Milky Way. They are fascinating objects because they are, by a huge margin, dominated by dark matter. They contain very few stars and almost no gas, meaning they have very little of the messy astrophysical background that plagues observations of the galactic center. They are essentially pristine, ultra-dense balls of dark matter with a faint sprinkling of stars. This makes them incredibly clean laboratories. For over a decade, the Fermi LRT has been patiently staring at these dwarf galaxies, collecting every single gamma-ray photon they emit. The process is a statistical marathon. Scientists combine the data from many different dwarfs, stacking their signals to look for a faint, collective bump of gamma rays at a specific energy that stands out above the expected background. It's a bit like trying to hear a single, faint note that is played very quietly by many different instruments in an orchestra. Individually, you can't be sure, but if you combine them all, the note might emerge from the noise. While this painstaking work has yet to yield a definitive eureka, a moment discovery, it has been far from fruitless. The persistent null result from the dwarfs has placed some of the most stringent constraints yet on the properties of dark matter. It has effectively ruled out entire classes of particles that would have annihilated at rates higher than what Fermi observes. Each year of data pushes the possible hiding spots for dark matter into narrower and more refined corners of parameter space. The absence of a signal is itself a powerful clue, telling us that if dark matter does annihilate, it does so at a rate much slower than many of the most popular models had predicted. This indirect search, looking for the ghostly aftermath of collisions we cannot see directly, continues to be a cornerstone of the hunt, a testament to the ingenuity of scientists using the cosmos itself as their ultimate detector. While we search the skies and listen in the deep silence underground, another grand effort to uncover dark matter's secrets is taking place at the largest machine ever built by humanity. Buried beneath the border between France and Switzerland, the Large Hadron Collider, or LHC, offers a completely different strategy. If we can't find dark matter out there in the cosmos, perhaps we can create it right here on Earth. This 27-kilometer ring of supercooled magnets and ultra-precise detectors is essentially a time machine designed to recreate the conditions that existed just a fraction of a second after the Big Bang. By accelerating protons to 99.999999% the speed of light and smashing them together head-on, the LHC concentrates an immense amount of energy into a vanishingly small point, briefly forging a fireball of primordial energy from which new, exotic particles can blink into existence. It was here that the long-sought Higgs boson was finally discovered in 2012, confirming a fundamental piece of our standard model of particle physics. Now, researchers are using the same incredible tool to hunt for something infinitely more elusive. The core idea is brilliantly simple. Einstein's famous equation, E equals mc squared, tells us that energy and matter are two sides of the same coin. By funneling enormous energy into these microscopic collisions, we can mint new coins transform pure energy into massive particles. The hope is that in this controlled chaos, amid the shower of known particles like quarks and electrons, something entirely new will be forged, including the potential constituents of dark matter. But this immediately presents a monumental challenge. How do you detect a particle that, by its very nature, does not interact with your detectors? If dark matter is truly invisible, sliding through ordinary matter like a ghost, it would leave no trace in the layers of sophisticated sensors that surround the LHC's collision points. It would simply escape the experiment entirely, completely unnoticed. This is where the concept of missing energy becomes the most important clue in the search. While we cannot see the dark matter particle itself, we can potentially see the hole it leaves behind. The process works like a cosmic accounting exercise. In a proton collision, the total energy and momentum of all the particles going into the smash is known with extreme precision. The laws of physics demand that the total energy and momentum coming out must exactly equal what went in. These quantities are always conserved. So, physicists meticulously catalog every single particle that erupts from the collision, measuring their energies and trajectories. They then add it all up. If the total energy of all the detected particles is less than the energy that was put into the collision, that deficit is the smoking gun. That missing energy must have been carried away by something that escaped detection entirely, an invisible particle that took its share of the momentum and flew away without a trace. In the intricate plots and graphs generated by experiments like a TLS and CMS, a significant spike of events with such an energy imbalance would be the first tantalizing hint of dark matter's production. Of course, it's not quite that straightforward. There are many mundane reasons why energy might appear to be missing. A neutrino, for instance, is a known standard model particle that interacts so weakly it will also escape the detector unnoticed, creating a false signal. Scientists must use incredibly complex statistical models to subtract these known backgrounds, searching for an excess of missing energy events that cannot be explained by any conventional process. They also look for the specific monojet or monophoton signatures that could accompany dark matter. In this scenario, if the dark matter particles are produced, they might be kicked out alongside a single, powerful jet of quarks and gluons or a high-energy photon that recoils against the invisible stuff. This single, energetic recoil object, balanced by nothing on the other side, is the detectable signpost pointing directly to the presence of the invisible. The beauty of the collider approach is how it perfectly complements the other search methods. Direct detection experiments deep underground are listening for the gentle whisper of a dark matter particle from our galactic halo bumping into an atom. Indirect detection telescopes like Fermi are scanning the skies for the loud flash of two dark particles annihilating each other in the void of space. The LHC, by contrast, is actively trying to produce dark matter in the lab. Each method probes different aspects of the particle's potential nature, its mass, how it interacts, and its cross-section. A discovery in one would not make the others obsolete. Instead, it would provide the crucial clues needed to refine the other searches. If the LHC were to find a hint of a new particle, it could tell direct detection experiments exactly what mass range to focus on with greater sensitivity. Conversely, if a direct detection experiment ever registers a clear signal, it would give collider physicists a specific target to aim for, allowing them to fine-tune their collisions to produce that very same particle and study its properties in detail. So far, like all the other searches, the LHC has not yet found conclusive evidence for dark matter production. With each increase in collision energy and each new set of data, it has ruled out more possibilities, narrowing the window for where these particles could be hiding. Yet the hunt continues with undiminished intensity. The collider represents a fundamentally different kind of courage in our quest to understand the universe. It is the courage not just to observe nature's secrets, but to try and wrestle them into the light through sheer force of will and ingenuity, recreating the universe's first moments in a desperate, glorious attempt to see what was forged in that ancient fire. But just as we thought we had the universe's recipe perfectly measured, a troubling discrepancy began to emerge, one so persistent that it now threatens to unravel our entire understanding of cosmic evolution. This is the Hubble tension, and it represents one of the most significant and puzzling mysteries in modern cosmology. The problem centers on the Hubble constant, a number that describes the current expansion rate of the universe. For decades, we've had two primary methods for pinning down this critical value, and they have always been in reasonable agreement. But as our measurements have become exquisitely more precise, a strange thing has happened. The two values have not converged. Instead, they have stubbornly refused to meet, creating a gap that grows wider with each new, more accurate observation. It's as if two of the most trusted clocks in the universe are ticking at undeniably different speeds, and no one can figure out why. One method of telling this cosmic time looks back to the very beginning, using that ancient afterglow of the Big Bang, the cosmic microwave background. The Planck satellite mapped the faint temperature variations in this radiation with incredible detail. And because those fluctuations are a frozen record of the universe's infancy, they encode its entire history of expansion. By plugging the precise measurements of these ripples into our standard model of cosmology, which includes dark energy and dark matter, we can run the clock forward and predict what the expansion rate should be today. This method gives us a very specific value for the Hubble constant. The other method skips the ancient history and measures the expansion rate directly in our local, modern universe. Astronomers use what are called the cosmic distance ladder. They start with nearby stars like Cepheid variables whose brightness pulses at a rate directly tied to their true luminosity. By measuring how bright they appear, we can calculate their exact distance. Then, they use these stars to calibrate the distance to more faraway galaxies that host Type 1a supernova. Since we know the true brightness of these supernovae, they become brilliant standard candles for measuring vast distances across space. By comparing these distances to the redshift of the galaxies, how much their light has been stretched by the expanding universe, scientists can directly calculate the current expansion rate. The conflict arises because these two methods, both executed with meticulous care and cutting-edge technology, keep giving us different answers. The Planck measurement from the early universe suggests an expansion rate of about 67.4 kilometers per second per megaparsec. This means that for every megaparsec, a distance of about 3.3 million light-years, a galaxy is moving away from us at 67.4 kilometers per second faster. But the local measurements using supernova and Cepheids consistently find a higher value, around 73 kilometers per second per megaparsec. The universe appears to be expanding roughly 9% faster today than our best model of the early universe predicts it should be. This might sound like a small difference, but the uncertainties in these measurements have now been shrunk so small that the gap between them is over 5 sigma, a statistical threshold that in particle physics is considered a definitive discovery. This isn't an error, it's a real and glaring inconsistency. This tension has forced cosmologists to confront a terrifying and exciting possibility that our standard model of cosmology, the lambda CDM model that has been so successful, might be incomplete. We may be missing a crucial ingredient. The hunt is now on for what that could be. Perhaps dark energy is not a simple cosmological constant, but something dynamic that has evolved over time, growing stronger and accelerating the expansion more than we anticipated. This idea, called quintessence, proposes a new, evolving field that could account for the faster modern expansion. Or maybe dark matter has properties we haven't yet accounted for. It could interact with itself or with dark energy in some unknown way that changes the expansion history. Another radical suggestion is that the early universe was somehow different, perhaps with a brief period of even faster expansion that left an imprint we're misinterpreting. Some have even proposed that we live in a rare underdensity in the cosmos, a giant cosmic void that is locally distorting our measurements, though this seems increasingly unlikely. The most profound implication is that this tension could be our first tangible clue pointing toward new physics beyond our current understanding. It's a crack in the foundation of our model, and through that crack, we might finally catch a glimpse of the deeper truths governing dark energy and the ultimate fate of everything. Resolving the Hubble tension is now one of the highest priorities in astronomy, driving the development of powerful new telescopes and surveys designed to measure the expansion rate with even greater precision. It's a mystery that reminds us that the universe still holds profound secrets, and our journey to understand it is far from over. So we've mapped the universe's expansion history and found it's accelerating, driven by this mysterious dark energy. But simply giving it a name isn't enough. To truly understand what it is, we need to describe its character, its behavior. How does it push the cosmos apart? The key to unlocking this lies in a single, deceptively simple number, a parameter that cosmologists call its equation of state, represented by the letter W. This number is essentially the ratio of the pressure that dark energy exerts to its energy density. Now, for most stuff we're familiar with, this concept is pretty straightforward. For ordinary matter, like the atoms in a planet or a star, the pressure is negligible compared to its density, so W is essentially zero. For radiation, like light, the pressure is positive and equals 1/3 of its energy density, giving it a W of positive 1/3. These values make sense within our normal experience of physics, but dark energy is different. It's a property of space itself, and to cause the expansion of the universe to accelerate, it must exert a negative pressure, a sort of gravitational repulsion. This is where the value of W becomes absolutely critical. The simplest and most elegant explanation for dark energy is Einstein's old cosmological constant, the idea that empty space has a fixed, immutable energy density. In this model, the pressure is exactly equal to the negative of that energy density. Do the math on that ratio, pressure divided by density, and you get a value of W equals -1. A universe with this value would expand in a very particular way, with the acceleration becoming more dominant over time in a smooth, predictable fashion. This is the foundation of our standard model of cosmology. But what if dark energy isn't this simple? What if it's not a constant at all, but a dynamic field that changes over time, something physicists call quintessence? This idea opens up a universe of possibilities. If dark energy is a dynamic field, its energy density could slowly dilute or increase as the universe expands, and its pressure could change along with it. This would mean its equation of state, its W value, would not be exactly -1. It could be slightly greater than -1, or perhaps even slightly less. That tiny deviation would be an absolute revolution in physics, because it would mean dark energy is evolving. It has a history. It's something we could potentially understand and maybe even connect to other fields in particle physics. This is why measuring W and pinning down its value with excruciating precision is one of the most important goals in all of cosmology. It's not about just confirming a number, it's about distinguishing between two profoundly different visions of reality. Is the cosmos fueled by a steady, unchanging vacuum energy, or is it driven by a cosmic field that's still unfolding and changing? To find out, astronomers don't use a single instrument. They combine multiple techniques in a powerful cross-check. They look back at the ancient universe using the cosmic microwave background from Planck, which gives us a snapshot of the expansion rate billions of years ago. Then they measure the more recent expansion history by charting the distances to thousands of Type Ia supernova, those brilliant standard candles, by comparing how the expansion rate has changed over this immense cosmic timeline. They can triangulate the value of W. It's a delicate statistical process, and every decimal point matters. The latest results are incredibly precise, but they are also incredibly intriguing. The data consistently points to a value very, very close to -1, but it hasn't yet ruled out the possibility of a tiny deviation. The uncertainty in the measurement still allows for W to be something like -0.95 or -1.05. That window of possibility, though small, is where the next great discovery might be hiding. Finding a definitive deviation would be like hearing the universe change its tune after 14 billion years. A value greater than -1 would strongly suggest a dynamic form of dark energy like quintessence, a field that weakens over time. A value less than -1, often called phantom dark energy, would be even more bizarre and unsettling. This scenario would imply that the energy density of dark energy actually increases as the universe expands, leading to a future so violent it could eventually tear apart every single atom, every nucleus, in a final cataclysm known as the Big Rip. The hunt for the true value of W is therefore a journey to foretell the ultimate fate of everything. Current and future observatories like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope are designed specifically for this task. They will map billions of galaxies and discover millions of supernova, shrinking the error bars on W to a razor's edge. They are not just looking to confirm the standard model, they are actively searching for a crack in it, a sign that the cosmos is even stranger and more dynamic than we ever imagined. This brings us to one of the most profound questions we can ask. Where is all this headed? The ultimate fate of our entire universe hinges entirely on the true nature of dark energy, and cosmologists have outlined 3 deeply compelling and deeply contrasting scenarios for how the cosmic story might end. The first, and based on our current best measurements, most likely scenario is known as the heat death or the Big Freeze. This future assumes that dark energy is indeed a cosmological constant, with its equation of state fixed firmly at W equals -1. In this case, the accelerated expansion we see today will continue indefinitely, forever gaining momentum. Billions of years from now, the consequences will begin to compound in truly staggering ways. First, our local group of galaxies will have long since merged into a single, giant elliptical galaxy, but everything beyond that will have vanished from sight. The expansion of space will have stretched the fabric of the cosmos so much that the light from all other galaxies will be redshifted into oblivion, their photons stretched to wavelengths longer than the observable universe itself. The sky, which is currently filled with the faint glow of the cosmic microwave background, will become utterly black and empty. The universe will be a profoundly lonely place. As eons turn into eons, the accelerated expansion will begin to tear apart the very fabric of gravity-bound structures. First, the gravitational bonds holding galaxy clusters together will be overcome, and the clusters will drift apart. Then, individual galaxies will be pulled apart. Eventually, even star systems will be severed, and planets will be ripped from their orbits around dead stars. In the final, chilling stages, the relentless expansion could potentially overcome the forces holding atoms themselves together, though this requires a phantom energy scenario. Long before that, all star formation will have ceased as the raw material for new stars is diluted into an ever-expanding void. The last stars will flicker out, and the universe will be left with nothing but a sparse, ever-cooling soup of subatomic particles and black holes. And even those black holes will not last forever. Through a process known as Hawking radiation, they will incredibly slowly evaporate, returning their mass to the vacuum over timescales so vast they defy human comprehension. The final state is a universe at absolute zero, a static, silent, and eternal equilibrium where nothing ever happens again. It is a quiet, cold, and desolate end. The second possibility is far more violent and dramatic, the Big Rip. This fate awaits us if dark energy is not a constant but something far more sinister, a form of phantom dark energy where its equation of state is less than -1, meaning W is less than -1. In this model, the energy density of dark energy doesn't remain constant or dilute. It actually increases as the universe expands. This creates a terrifying positive feedback loop. More expansion creates more repulsive force, which drives faster expansion, which creates even more repulsive force. The acceleration wouldn't just continue, it would become exponentially more ferocious over time. In this scenario, the universe doesn't just become isolated and cold, it is literally torn to shreds. The disintegration would happen in a very specific, horrifying sequence, and we can actually calculate a potential timeline for the end of everything. First, the accelerating expansion would overcome the gravitational glue holding galaxy clusters together, and they would fly apart. Then, the force would become so strong that it would rip individual galaxies apart. As the repulsive force continues to strengthen, it would next target smaller structures. About 60 million years before the final cataclysm, the expansion would overcome the gravity holding our solar system together, flinging planets into the dark. Just months before the end, the force would be strong enough to pull planets apart. In the final minutes, stars and planets would be shredded, and in the last terrifying moments, the repulsive force would exceed the fundamental forces that bind atoms together, the electromagnetic force and even the strong nuclear force. Atomic nuclei would be vaporized, and every single piece of matter in the universe would be dissolved into a diffuse, disconnected cloud of elementary particles, unable to ever interact again. The universe would meet its end not with a whimper but with a definitive, violent tear in the fabric of spacetime itself. The third classic possibility offers a very different ending, the Big Crunch. This was the favored model for most of the 20th century before the discovery of dark energy. It envisions a universe where the density of matter is so high that the collective pull of gravity eventually halts the expansion, reverses it, and pulls everything back together. For this to happen, dark energy would have to be neither constant nor phantom, but a dynamic field that actually fades away over time, losing its repulsive power. If that were to happen, gravity would once again become the dominant force on cosmic scales. The expansion would slow, stop, and then the great contraction would begin. Galaxies would start to move toward each other, their light blue-shifted as space itself shrinks. The temperature of the cosmic microwave background would begin to rise as the universe gets smaller and denser. The sky would grow hotter and brighter. Eventually, all the galaxies would collide and merge, and the universe would revert to a hot, dense state mirroring its beginning. In some versions, this collapse culminates in a giant singularity, a reverse of the Big Bang that ends all of spacetime. Some theoretical models even suggest this could be part of an endless cycle, a big bounce, where the universe collapses and then rebounds into a new expansion phase forever. However, with our current evidence for accelerating expansion, the Big Crunch has become the least likely of the three fates, a relic of an older understanding of the cosmos that now seems increasingly distant. The choice between these three futures, the silent freeze, the violent rip, or the crushing reversal, rests entirely on the precise value of W, that critical equation of state for dark energy. Our current measurements point toward the Big Freeze, but the uncertainty in that measurement is the most important uncertainty in all of cosmology. It is the difference between a universe that ends in isolated silence and one that ends in catastrophic rupture. Determining which path we are on is perhaps the greatest scientific endeavor of our age, a quest to read the final chapter of the universe by understanding the mysterious dark energy that writes it. But if dark matter provided the invisible scaffolding for galaxies and clusters, its influence did not stop there. The true grandeur of its architecture is revealed not when we look at individual structures, but when we pull back to see the universe on its very largest scales. When astronomers began mapping the positions of millions of galaxies in the late 20th century, they didn't find a random, scattered distribution. Instead, they uncovered an intricate, almost biological-looking network, a vast cosmic web of unimaginable scale and complexity. This is the large-scale structure of the universe, and it is perhaps the most dramatic and visible testament to the power of dark matter's gravitational pull. This cosmic web is a tapestry woven from three primary elements. First, there are the dense nodes where giant galaxy clusters reside, the bustling metropolises of the cosmos. These are interconnected by long, slender filaments, like vast cosmic highways made of galaxies and gas that can stretch for hundreds of millions of light years. Between these filaments are great walls, which are flat, sheet-like arrangements of galaxies. And finally, there are the voids, enormous, nearly empty bubbles of space that can be hundreds of millions of light years across, constituting the majority of the universe's volume. This entire structure resembles a sponge or a network of neurons, a fractal pattern of matter and emptiness that repeats itself across the observable universe. The question is, how did such an intricate pattern emerge from the nearly smooth, hot soup of the Big Bang? The answer, once again, lies with the dark matter. The tiny fluctuations in density first imprinted in the cosmic microwave background were the seeds from which this entire web grew. These minuscule overdensities, places where there was just a tiny bit more dark matter than average, had a gravitational advantage. They began to pull in more dark matter from their surroundings. As the universe expanded over billions of years, gravity acted as the master sculptor, amplifying these small initial differences. The dark matter flowed from the underdense regions, the future voids, into the overdense regions. This flow wasn't random. It happened most efficiently along specific paths, channeling dark matter into the evolving network of filaments. The nodes formed at the intersections of these filaments, where the gravitational wells were deepest and could pull in the most material. The ordinary matter, the gas made of atoms, was simply a passenger on this gravitational journey. It followed the dark matter into the wells and filaments, eventually cooling and collapsing to form the galaxies we see tracing out the web today. Mapping this structure has become a primary goal of modern astronomy, achieved through immense projects like the Sloan Digital Sky Survey. By meticulously measuring the three-dimensional positions of countless galaxies, scientists can create a chart of this cosmic geography. This map is more than just a pretty picture, it is a powerful forensic tool. The precise statistical properties of the web, the sizes of the voids, the thickness of the filaments, the spacing between clusters, are a direct record of the properties of the dark matter that built it. For instance, the fact that we see such a well-defined filamentary web tells us that dark matter must be cold. This doesn't refer to its temperature, but to its velocity. Cold dark matter moves relatively slowly, which allows it to clump together easily on small scales first, eventually building up to the gigantic structures we see. A hot dark matter candidate, like a fast-moving neutrino, would have washed out these small-scale fluctuations, preventing the formation of the fine details of the web and resulting in a much smoother, blobby universe. The existence of the sharp, delicate filaments we observe is therefore a strong argument in favor of cold dark matter. Furthermore, by comparing these detailed maps of the present-day web to the blueprint of the early universe from the CMB, cosmologists can trace the entire history of cosmic structure formation. They can see how gravity has magnified the initial seeds over 13.8 billion years. This allows them to test our models of the universe with incredible precision, constraining the exact amount of dark matter and its behavior. Any deviation from the predictions could be a sign of something new. Perhaps that dark matter has some unknown interaction beyond gravity, or that our understanding of gravity itself needs tweaking on these colossal scales. The cosmic web is the ultimate expression of dark matter's hidden influence, a ghostly architecture built by an unseen hand, whose final blueprint we are only now beginning to decipher. But perhaps the most precise of these cosmic rulers wasn't forged in any stellar furnace, but was instead imprinted upon the fabric of the universe itself during its first turbulent moments. We've already seen how the cosmic microwave background gives us a snapshot of the infant cosmos, but the story doesn't end with that frozen flash of light. The same physics that created those temperature variations also set in motion colossal sound waves that raced through the primordial plasma, and the echo of those waves can still be found today, providing an exquisitely precise tool for measuring the expansion of the universe. This phenomenon is known as baryon acoustic oscillations, and it offers us a completely independent way to probe the influence of dark energy across billions of years of cosmic history. To understand this, let's journey back to that hot, dense plasma that filled the universe before it became transparent. It wasn't a smooth, uniform soup, it was rippling with turbulence. At the heart of this chaos was a fundamental tug of war. On one side, you had gravity relentlessly trying to pull matter, both the ordinary baryonic matter, protons and neutrons, and the dark matter into denser clumps. Pushing back with immense force was radiation pressure, primarily from the countless photons of light that were constantly bouncing off the free electrons, creating an outward pressure that resisted gravity's pull. This created a powerful oscillation, like a spring being compressed and released. A region of slightly higher density would begin to collapse under its own gravity, but as it compressed, the radiation pressure inside would skyrocket, becoming so intense that it would halt the collapse and violently push the matter back outward. This created a spherical sound wave, a shell of compressed matter and radiation that expanded outward from the initial overdense seed at a significant fraction of the speed of light. These weren't gentle ripples, they were the most powerful sound waves in history, booming across the entire universe, but this cosmic concert couldn't last forever. The critical moment came about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. In an instant, the free electrons were captured and the fog cleared. The photons, which had been providing the radiation pressure, suddenly raced off in all directions, eventually becoming the cosmic microwave background we detect today. Without that radiation pressure to push back, the sound waves stopped dead in their tracks. The waves froze instantly, leaving behind a lasting imprint. Each of those initial overdense regions was now surrounded by a single, fossilized spherical shell of matter, a shell that had traveled a very specific distance before the music stopped. This distance, about 500,000 light-years across at that time, became a permanent standard ruler etched into the distribution of matter. Now, fast forward billions of years, gravity has been at work the entire time, pulling that matter into the galaxies and clusters we see today. But that process didn't erase that ancient pattern, it preserved it. The result is that galaxies today are ever so slightly more likely to be separated from each other by a specific distance, the size of that fossilized shell, stretched to a colossal scale by the expansion of the universe. Imagine the universe is dotted with billions of these invisible spheres, all the same size. If you were to take a massive census of galaxies and measure the distances between them, you would find a small but statistically significant excess of galaxy pairs separated by this special scale. It's not that every pair of galaxies is this distance apart. It's that this specific separation is more common than any other, creating a faint but detectable peak in the statistical distribution of galaxies. This is the baryon acoustic oscillation signal, a ghostly echo of the universe's first sound, now frozen in the large-scale structure of the cosmic web. For cosmologists, this is a gift of unparalleled precision. That BAO scale is a known quantity. We know its true size from the physics of the early universe, which we understand extremely well from the CMB. By then measuring its apparent size in the sky at different epochs, by looking at galaxy maps from the distant past, the recent past, and the present, we can do something remarkable. We can see how this standard ruler has been stretched by the expansion of the universe over billions of years. It acts as a calibration stick against which we can measure cosmic distances with incredible accuracy. When we look at a very distant, ancient collection of galaxies, the BAO peak appears smaller in angular size on the sky because it is very far away. When we look at a closer, more recent sample of galaxies, the same BAO peak appears larger because it is nearer to us. By measuring this apparent size at different redshifts, we can directly chart how the expansion rate of the universe has changed over time. This provides a powerful and completely independent check on the findings from supernova. The supernova measurements revealed the acceleration, while the BAO measurements help us precisely characterize it. The two methods have different systematic uncertainties. Supernova rely on our understanding of stellar explosions, while BAO relies on pure geometry and the physics of the early universe. The fact that they both tell the same story, that the expansion is accelerating, and that the amount of acceleration aligns with a universe dominated by dark energy, provides a stunning cross-confirmation that makes the evidence overwhelmingly robust. Major galaxy redshift surveys, like the Baryon Oscillation Spectroscopic Survey (BOSS) and its successors, have spent years meticulously mapping the three-dimensional positions of millions of galaxies to detect this subtle statistical peak. Their results have not only confirmed the accelerated expansion but have gone further, helping to constrain the properties of dark energy and measure its equation of state with ever-increasing precision, solidifying our understanding of the mysterious force that is shaping the ultimate fate of everything. But this elegant picture of a universe sculpted by cold, collisionless dark matter is not without its own puzzles. As our simulations grew more sophisticated and our observations more precise, a subtle but persistent discord emerged, centered not on the vast cosmic web, but deep within the heart of individual galaxies. This is the cusp versus core problem, a technical-sounding mystery that strikes at the very heart of our understanding of how dark matter behaves on the smallest scales. According to the wildly successful Lambda CDM model, the dark matter halos that form around galaxies should have a very specific density profile. The simulations consistently show that density should rise steeply and smoothly toward the galactic center, forming a sharp peak or a cusp. This makes intuitive gravitational sense. The pull of gravity is strongest at the center, so that's where you'd expect the dark matter to be most densely packed. However, when astronomers set out to test this prediction by studying the motions of stars and gas within real, nearby dwarf galaxies, they found something startlingly different. Instead of a steep rise in density, the data suggested the dark matter distribution was much flatter in the center, forming a constant density core. It was as if the very center of these dark matter halos had been scooped out. Dwarf galaxies are the perfect laboratories for this investigation because they are overwhelmingly dominated by dark matter, with very little messy astrophysics from stars and gas to complicate the gravitational measurements. The evidence from these small, faint galaxies was difficult to ignore and pointed to a clear discrepancy. What the supercomputers simulated and what the telescopes observed were two fundamentally different things. This anomaly wasn't just confined to a few quirky dwarfs. Even in the rotation curves of some larger, low-surface brightness spiral galaxies, the telltale signature of a dark matter core seemed to appear. The gravitational pull in the inner regions was weaker than the simulations predicted, indicating less dark matter was concentrated there than expected. This core cusp problem became one of the most significant small-scale challenges for the standard dark matter model, forcing physicists to consider two broad possibilities. Either there was something wrong with our understanding of the dark matter itself, or there was something significant happening within galaxies that the simulations were missing. The first possibility is the most thrilling. It suggests that dark matter is not the simple, collisionless particle we've assumed it to be. Perhaps it possesses a small but meaningful ability to interact with itself through some unknown force, not just through gravity. If dark matter particles could bump into each other, even very rarely, it would act as a form of friction. This self-interaction could potentially smooth out the dense central cusp, transferring energy from the inner particles to the outer ones and effectively eroding the sharp peak into a gentler, flatter core. Alternatively, if dark matter were somehow warmer and moved faster in the early universe, it could have resisted collapsing into such tight, cuspy centers in the smallest galaxies. These ideas push the boundaries of particle physics and open the door to a richer, more complex dark sector. The second possibility places the blame not on dark matter, but on the ordinary matter that we thought was just along for the ride. This explanation invokes a process known as baryonic feedback. The word baryonic refers to normal atomic matter, and feedback describes how the intense activity of stars can dramatically alter their environment. In the early lives of galaxies, especially small ones, periods of furious star formation would have been punctuated by colossal supernova explosions. These stellar cataclysms don't just light up the sky, they inject enormous amounts of energy into the surrounding gas, creating powerful winds that blow outward from the galactic center. This outburst of energy can literally push the gas around, and because the gas is tied to the galaxy's overall gravitational field, this dramatic rearrangement of ordinary matter can, in turn, pull and drag on the dark matter itself. The gravitational potential well at the center changes shape, and the dark matter particles respond by migrating outward, effectively heating up and expanding away from the core, thus flattening the central density. It's a fascinating case of the tail wagging the dog, where the 5% of the universe we can see might be responsible for sculpting the distribution of the 27% we cannot. Resolving this mystery is an active front in astrophysical research, requiring ever more detailed simulations that now try to incorporate the complex, explosive effects of star formation and supernova. The latest models are beginning to show that this baryonic feedback can indeed create cores in dwarf galaxies, potentially reconciling the theory with the observations. Yet the question is not fully settled. The debate between self-interacting dark matter and complex baryonic physics continues to drive our exploration, proving that even the most successful cosmic models must constantly be tested against the nuanced and often surprising reality of the universe we observe. Even as we grapple with the core cusp mystery within individual galaxies, another startling contradiction emerges when we zoom out to look at the family of galaxies orbiting our own Milky Way. This puzzle, known as the too big to fail problem, sounds like it belongs on Wall Street, but it's actually one of the most perplexing issues in modern cosmology. It all started when our supercomputer simulations of cosmic structure, which have been so successful on large scales, began making a very specific prediction about our own galactic neighborhood. These incredibly detailed models, which trace the formation of galaxies and their dark matter halos, suggested that the most massive subhalos of dark matter orbiting the Milky Way should be powerful enough. Their gravitational wells should be so deep that they could easily hold onto vast amounts of gas and form bright, sizable satellite galaxies. The simulations predicted we should be surrounded by a retinue of perhaps a dozen or more of these large, luminous satellite galaxies. But when astronomers went to take a census, the actual number was startlingly low. We only observe a handful of large satellites like the Large and Small Magellanic Clouds, and then a collection of much smaller, fainter dwarf galaxies. The most massive satellites that the simulations insist should be there, shining brightly in our sky, appear to be completely missing. It's as if the universe failed to build the very giants it was supposed to, hence the name too big to fail. These dark matter halos were too massive to have failed at forming prominent galaxies. The heart of the problem lies in the connection between the dark matter we cannot see and the luminous galaxies we can. The simulations show a population of dense, massive dark matter subhalos that simply have no luminous counterparts in the real world. They are massive enough that the gas falling into them should have cooled, condensed, and ignited star formation, creating a galaxy that would be easily visible to us. Their absence is a glaring hole in our understanding. One of the first proposed solutions was that perhaps our own Milky Way is unusual, an outlier in a mostly predictable cosmos. But the same discrepancy has now been observed around our nearest large galactic neighbor, Andromeda. It too has fewer large satellite galaxies than the simulations predict. This suggests the too big to fail problem isn't just a fluke of our local environment. It might be a fundamental issue with the lambda CDM model itself on these relatively small scales. This has forced scientists to consider some radical possibilities. Perhaps our understanding of how galaxies form within these dark matter halos is incomplete. Maybe a process like reionization, the moment when the first stars and galaxies flooded the universe with ultraviolet light, was more effective than we thought at sterilizing these small halos. The intense UV radiation could have heated the gas in the smallest halos, preventing it from cooling and collapsing to form stars, leaving the dark matter halo permanently dark and invisible. Alternatively, perhaps supernova explosions in the very first generations of stars were so violent that they blew all the star-forming gas out of these small halos early on, again stranding them as failed galaxies. But the more exciting possibility is that this is another clue pointing toward the intrinsic nature of dark matter. The standard model assumes dark matter is cold and collisionless particles that move slowly and mostly pass right through each other. But what if that's not entirely true? If dark matter had even a small ability to interact with itself through some force other than gravity, it could dramatically change the structure of these small halos. Self-interacting dark matter would act like a form of friction, smoothing out the densest central regions of halos and making them less centrally concentrated. A less dense core would mean a weaker gravitational pull, making it much easier for energetic processes like supernova to blow the gas out entirely, preventing a bright galaxy from ever forming. This would explain why we see the dark matter halos in simulations, but not the galaxies. The halos might be there, but they've been puffed up and rendered incapable of galaxy formation. The too big to fail problem, therefore, isn't just a small anomaly. It's a potential window into the hidden physics of the dark sector, suggesting that the invisible majority of the universe might be more complex and dynamic than we ever imagined. But what if the answer to these small-scale puzzles isn't found in the complex astrophysics of stars, but in the hidden nature of dark matter itself? For decades, the simplest assumption has been that dark matter is collisionless. Its particles only influence each other and the outside world through the force of gravity, passing through everything like silent, non-interacting ghosts. This model, known as cold, collisionless dark matter, has been spectacularly successful at explaining the universe on the largest scales, from the cosmic microwave background to the vast filamentary web of galaxies. Yet, its apparent failures on smaller scales, like the missing dwarf galaxies and the puzzlingly flat cores within them, have prompted physicists to consider a more radical idea, that dark matter might not be entirely solitary. This brings us to the compelling possibility of self-interacting dark matter, or SIDM. Imagine if dark matter particles could interact with each other through a new, unknown force, a kind of dark force that operates solely within the hidden sector of the universe. This wouldn't be like the electromagnetic force that makes things stick together or repel. It would be a force that only dark matter feels. In this scenario, when two dark matter particles pass close to one another, they could occasionally scatter off each other, much like billiard balls colliding on a table. This self-interaction would introduce a form of friction and energy transfer within a dark matter halo. In the dense central regions of a galaxy where particles are packed tightly together, these collisions would be more frequent. The effect would be to smooth out the extreme density peak, transferring heat from the hotter, faster-moving particles in the center to the cooler outskirts. Over time, this process would naturally erode the sharp theoretical cusp into an observed, flatter core, directly addressing one of the most persistent small-scale problems. Furthermore, in the smallest, faintest dark matter halos, this same process could puff them up, making their gravitational wells shallower and preventing them from easily holding onto the gas needed to form bright stars. This would elegantly explain the too-big-to-fail problem, as many of those massive but dark subhalos would simply fail to ever light up, remaining as invisible, ghostly satellites. Of course, introducing a new fundamental force is a massive step, and any credible theory must survive confrontation with hard evidence. This is where observations of galaxy clusters, particularly dramatic collisions like the Bullet Cluster, become absolutely crucial. Recall that the Bullet Cluster provided a stunning visual proof of dark matter's existence because the gravitational lensing map showed the mass was separated from the visible gas. This happened precisely because the clouds of colliding gas slammed into each other and slowed down, while the dark matter, which does not interact with that gas, sailed right through. For the self-interacting dark matter model, this presents a critical test. If dark matter particles interact with each other, even weakly, then during a massive cluster collision, they shouldn't pass through completely unscathed. There should be some discernible effect, a slight slowing down, a detectable offset, or a telltale shape to the dark matter distribution that differs from the purely collisionless prediction. Remarkably, the Bullet Cluster and other similar systems place incredibly tight constraints on just how strong this self-interaction can be. By meticulously analyzing the dynamics of these cosmic crashes, physicists can calculate the self-interaction cross-section, essentially, the probability that two dark matter particles will scatter when they meet. The results from these observations tell us that any such interaction must be exceptionally weak. The allowed cross-section is incredibly small, meaning that while dark matter might have a tiny ability to interact with itself, it is nowhere near strong enough to be the sole solution for all the small-scale issues. It's a delicate balancing act. The self-interaction needs to be strong enough to solve the problems in dwarf galaxies, but weak enough to not disrupt the clean, collisionless behavior we observe in larger, faster-moving galaxy clusters. This has led to more nuanced models where the self-interaction strength might depend on the relative velocity of the particles, being more effective in the slower-moving, calmer environments of dwarf galaxies than in the violent, high-speed collisions of massive clusters. The investigation into self-interacting dark matter is a beautiful example of the scientific process at work. It starts with an anomaly in the data, proposes a bold new hypothesis to explain it, and then subjects that hypothesis to the most rigorous experimental tests imaginable. While the evidence so far suggests that dark matter is predominantly collisionless, the door is still open for a small, subtle level of self-interaction that could be the key to unraveling the remaining mysteries on the smallest galactic scales. It challenges us to consider that the dark sector might not be a monolithic, simple void, but a rich and complex world with its own hidden physics, forever influencing the universe we see in ways we are only just beginning to perceive. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole, a gravitational monster weighing millions or even billions of times more than our Sun. These cosmic giants seem to have been present since the universe's infancy, a fact that presents a monumental puzzle. How did such incredibly massive objects form so quickly after the Big Bang? The standard model of star collapse and growth through accretion struggles to explain how they had enough time to reach such staggering sizes. This has led scientists to look for a hidden catalyst, a mechanism that could give these black holes a colossal head start. One of the most compelling and controversial ideas is that the invisible hand of dark matter may have played a crucial role in their birth. The theory suggests that in the very early universe, even before the first stars ignited, vast clouds of dark matter were already collapsing under their own gravity, forming those deep potential wells that would eventually become galaxies. Within these dense primordial halos, the dark matter could have reached such incredible densities at the center that it triggered a direct collapse. Imagine the very first structure in the cosmos not being a star but a massive seed of pure gravity. Instead of a star dying and leaving behind a stellar mass black hole, a gigantic knot of dark matter could have collapsed in on itself, instantly creating a black hole with the mass of thousands of suns. This massive seed would then have had a tremendous gravitational advantage, immediately beginning to voraciously devour the infalling gas from the surrounding halo, ballooning in size at a breathtaking rate and quickly reaching supermassive status. This dark matter direct collapse provides an elegant solution to the timing problem, creating the massive seeds needed for the black holes we see in the early universe. But this idea invites an even more radical proposition, turning the entire mystery on its head. Could some or even all of the dark matter itself be black holes? This concept points to a hypothetical class of objects known as primordial black holes. Unlike the black holes formed from dying stars, primordial black holes are thought to have been forged in the extreme density fluctuations of the universe's first second, a time of unimaginable heat and pressure. They wouldn't be the end result of a star's life, but relics of creation itself, and their masses could range from smaller than an atom to larger than a star. If vast numbers of these primordial black holes were created and have been drifting through the cosmos ever since, their collective gravitational pull could account for the effects we attribute to particle-based dark matter. They are, by their very nature, completely dark unless they are actively feeding, making them the ultimate invisible matter. The appeal of this idea was significantly boosted by a series of stunning discoveries made by the LIGO and Virgo gravitational wave observatories. These instruments began detecting ripples in space-time caused by the mergers of black holes, but many of these black holes were curiously heavy, falling in a mass range that is difficult to explain through standard stellar evolution. Could these be primordial black holes, survivors from the dawn of time? If so, they could constitute a significant portion of the dark matter permeating the galactic halo. However, this tantalizing possibility faces serious observational challenges. If the universe were teeming with enough primordial black holes to account for all the dark matter, they would leave noticeable imprints on the cosmos. They would frequently pass in front of distant stars, causing a detectable temporary brightening through gravitational microlensing. Extensive surveys looking for these events have not found nearly enough to support the idea that all dark matter is made of black holes of any particular mass. Furthermore, a dense population of smaller primordial black holes would have disrupted the delicate, precise pattern of the cosmic microwave background or torn apart the fragile, wide binary star systems we observe. The constraints are tight, suggesting that while primordial black holes might exist and contribute a fraction of the dark matter, they are unlikely to be the sole solution. This leaves us with a fascinating duality. On one hand, dark matter as a particle could have been the essential architect that built the earliest and largest black holes. On the other, black holes themselves, primordial ones, could be a component of the dark matter. These are not necessarily mutually exclusive ideas. The universe could easily be employing both mechanisms. The ongoing search involves scrutinizing the smallest, darkest dwarf galaxies for the presence of unexpectedly massive black holes. a sign that dark matter dynamics might have planted them there. It also involves ever more sensitive microlensing surveys and detailed studies of the cosmic microwave background, all hunting for the ghostly signatures of these ancient gravitational traps. The connection between dark matter and black holes represents a frontier where the laws of the very large and the very small collide, and where solving one profound cosmic mystery might just provide the key to unlocking the other. If dark matter represents a profound gap in our understanding of the cosmos, the enigma of dark energy is even more unsettling because it strikes at the very heart of physics itself. We have this incredibly precise measurement from Planck and other probes telling us that dark energy makes up about 68% of the universe, and that its energy density is a very specific, very tiny number. But when we try to calculate what that number should be using our best theories of the small-scale quantum world, we get an answer that is catastrophically, unimaginably wrong, a value up to 120 orders of magnitude too large. This isn't just a small error, it is the largest discrepancy between theory and observation in the entire history of science. It is a screaming alarm that our two most successful and powerful theories, quantum mechanics, which governs the atom, and general relativity, which describes the cosmos, are fundamentally, deeply incompatible. They cannot both be right in their current forms when it comes to the energy of the vacuum. Resolving this crisis requires a theory of everything, a framework that can finally unite gravity with the quantum realm. This is the ultimate goal of modern physics, and the leading candidates, string theory and loop quantum gravity, offer radically different, mind-bending ways to think about dark energy. String theory proposes that the fundamental building blocks of the universe are not point-like particles but incredibly tiny, vibrating strings. The different vibrational modes of these strings give rise to the different particles and forces we observe. One of the most profound implications of this theory is that it requires extra dimensions of space beyond the three we experience. To be mathematically consistent, string theory needs 10 or 11 dimensions. Our universe, then, would be a four-dimensional membrane, or brane, floating within a higher dimensional space. This introduces a fascinating possibility for explaining the vacuum energy. In string theory, what we perceive as the cosmological constant, the energy density of empty space, is not a fixed number but is determined by the way these extra dimensions are compactified, or curled up into a tiny, complex shape. The geometry of this hidden space, along with the arrangement of fields within it, defines the vacuum state and its energy. The problem and the potential solution is that string theory doesn't predict a single, unique vacuum. Instead, it predicts a colossal landscape of possibilities, perhaps 10 to the 500 or more distinct vacuum states, each with its own unique laws of physics and value for the cosmological constant. This landscape concept transforms the problem of dark energy's small value from a question of why to a question of where. In a multiverse populated by a near-infinite number of these different universes, most would have an enormous positive cosmological constant that would rip them apart instantly, or a large negative value that would cause them to collapse immediately. Only in an exceedingly rare subset of universes would the random roll of the dice yield a value as minuscule as the one we observe. In this view, our existence is itself the explanation. We could only find ourselves in a universe where the dark energy is small enough to allow galaxies, stars, and life to form. This anthropic reasoning is deeply controversial. For some, it is a profound Copernican shift, acknowledging that our universe is just one tiny part of a much larger and more diverse multiverse. For others, it feels like a retreat from the traditional goal of physics, to find a unique, predictive explanation for the constants of nature, not to rely on statistical chance and our own existence as the answer. Loop quantum gravity takes a completely different approach. It doesn't propose extra dimensions, but instead seeks to rewrite our understanding of spacetime itself at the smallest possible scale, the Planck length. In this theory, space is not smooth and continuous but is woven from a fabric of tiny, discrete, interconnected loops, a spin network. This quantum structure of space becomes especially important when considering the vacuum. The energy of empty space in the standard quantum view comes from these virtual particles flashing in and out of existence. But in loop quantum gravity, the very fabric of space has a finite graininess that might somehow suppress or cancel out these infinite contributions from all possible energy fields. It's as if the underlying pixelation of reality imposes a fundamental limit, preventing the vacuum energy from soaring to those impossible heights predicted by conventional quantum field theory. The challenge for loop quantum gravity is that it is still a work in progress. While it offers a compelling way to make sense of the geometry of space and has had remarkable success in modeling the singularity at the heart of a black hole and the beginning of the Big Bang, it has not yet produced a definitive, testable prediction for the value of the cosmological constant. It remains a powerful and elegant framework that might one day provide a unique, non-anthropic answer to the dark energy problem, but that day has not yet arrived. Whether through the vast cosmic lottery of string theory's landscape or the discrete woven space of loop quantum gravity, the quest for quantum gravity is ultimately a search for a deeper reality, one that can naturally explain why the universe is the way it is. The incredibly small but non-zero value of dark energy is not a minor detail. It is the central clue in this grand mystery. It is the number that determines whether the universe can foster life or not, and its precise value currently has no explanation within our established frameworks. Unifying quantum mechanics and gravity is the greatest intellectual adventure in physics, and solving the riddle of dark energy is the ultimate prize. It would do more than just complete our equation. It would reveal a new layer of cosmic truth, showing us how the quantum flicker of the very small is inextricably linked to the accelerating fate of the very large. This profound disconnect between theoretical prediction and observational reality, the vacuum catastrophe, forces us to confront the possibility that our very framework for understanding the universe is incomplete. It pushes cosmology into the deeply philosophical and controversial realm of the anthropic principle. This idea suggests that the fundamental constants of nature, including the value of dark energy, might not be uniquely determined by a beautiful, overarching theory. Instead, they could be accidental, environmental variables. In this view, our universe is just one tiny bubble in a vast, perhaps infinite, multiverse. Each of these countless universes could have its own randomly selected set of physical laws and constants. In the overwhelming majority of these universes, the cosmological constant would be enormous, causing space to expand so violently that matter is ripped apart before it can ever coalesce into atoms, let alone stars, planets, or people. Or it could be strongly negative, causing the universe to collapse back in on itself almost immediately in a big crunch. The key point is that only in an exceedingly rare subset of universes, by pure chance, would the value of the cosmological constant fall within the incredibly narrow window that allows for the formation of galaxies and the eventual emergence of conscious life. We find ourselves in such a universe not because it is special or predetermined, but simply because we could not possibly exist anywhere else. Our observation of this specific, life-permitting value is therefore a selection effect, not a profound clue to a unique fundamental law. This line of reasoning, while logically consistent, is deeply unsatisfying to many physicists. It can feel like a retreat from the traditional goal of science, which is to find deterministic, predictive explanations for why the universe is the way it is. Resorting to a multiverse and anthropic selection can seem like giving up, an admission that we will never find a deeper reason for the value of dark energy. Critics argue it is an untestable, almost metaphysical proposition that moves the problem into a realm beyond scientific verification. However, proponents counter that it might simply be a reflection of reality's true nature. that there is no deeper why for some constants, and that we must adjust our expectations of what a fundamental theory can predict. The debate touches on the very nature of scientific explanation itself. Are we searching for a single, elegant equation that uniquely defines our universe, or are we discovering that we inhabit a cosmic landscape of possibilities, a vast ensemble where every possible physical law is realized somewhere? The incredibly small, non-zero value of dark energy, so crucial for our existence yet so perplexing to our theories, remains the central piece of evidence in this profound philosophical struggle, a mystery that may ultimately reveal less about the cosmos and more about the limits of our own understanding. This cosmic story of dark matter is often told on the grandest scales, explaining how it built the vast architecture of galaxies and clusters that fill the observable universe. But this leads to a profoundly intimate and humbling question. What is dark matter's role in our own existence? Could it be that this invisible substance, which makes up the majority of all matter, was not just a passive spectator to the rise of life, but an active and essential participant? The answer appears to be a resounding yes, though not in the way you might imagine. Its contribution wasn't a gentle nudge but a foundational necessity, a cosmic prerequisite without which the universe would be a barren, lifeless void. To understand why, we need to rewind the clock to the universe's earliest moments. The initial conditions after the Big Bang were incredibly fine-tuned. The tiny density fluctuations imprinted in the cosmic microwave background were just the right amplitude, not too large, not too small. If they had been any stronger, the universe would have collapsed back on itself far too quickly. If they had been any weaker, matter would never have clumped together at all, forever diffusing into an ever-expanding emptiness. This is where dark matter's unique properties became the key ingredient for life. Because it does not interact with light or radiation, it was immune to the intense pressure that filled the early cosmos. This allowed it to begin collapsing under gravity long before ordinary matter could, providing the gravitational anchors, the seeds around which the first structures could form. Without this head start, the slight over-densities in the atomic matter would have been washed out by the pressure of radiation, preventing the gravitational collapse that leads to galaxies and stars. The universe would have remained a dark, ultra-diffuse sea of hydrogen and helium, with no planets, no chemistry, and no possibility for life to ever emerge. In this very real sense, every star, every planet, and every living thing is here because dark matter provided the indispensable scaffolding for the visible universe to be built upon. Beyond this foundational role, there are more speculative yet fascinating ways dark matter might have directly influenced the history of life on Earth. One compelling idea involves our solar system's journey through the Milky Way. Our galaxy is not static, it rotates, and our Sun, along with its planets, travels on a wavy orbit around the galactic center. This path periodically carries us through the galaxy's dense disk, where the concentration of stars, gas, and dark matter is highest. Some scientists have proposed that as we pass through these thicker regions, we might also be moving through denser clumps of dark matter in the galactic halo. Could this have any tangible effect? One hypothesis suggests that these encounters might subtly perturb the vast cloud of cometary material at the solar system's outer edge, the Oort cloud. A gravitational nudge from a concentrated clump of dark matter could dislodge comets, sending them on a long journey inward, potentially increasing the rate of comet impacts on Earth. While the evidence is far from conclusive, it's a captivating thought that the invisible hand of dark matter might have indirectly orchestrated cosmic events that influenced our planet's climate and the course of biological evolution, perhaps even contributing to mass extinction events that cleared the way for new life forms, including our mammalian ancestors. Another, even more exotic, possibility involves the nature of dark matter itself. If a small fraction of dark matter particles possess a tiny ability to interact with ordinary matter beyond gravity, Could they have played a direct role in earthly affairs? The vast majority of dark matter would stream through our planet completely unnoticed, but what if a rare interaction could transfer energy and generate heat? It has been proposed that if certain types of dark matter particles were captured by Earth's gravity, they could become trapped and accumulate in the planet's core. Over billions of years, the annihilations of these particles could provide a source of internal heating. This exotic form of geothermal energy might even help explain the persistent warmth of Earth's interior, which drives plate tectonics, a process many scientists believe is crucial for maintaining a stable climate and recycling nutrients essential for life. While this remains a highly speculative idea, it underscores a profound shift in perspective. Dark matter is not just an abstract concept for cosmologists. It may be an intimate part of our world, woven into the very fabric of our planet, and by extension, the story of how a seemingly insignificant rocky world orbiting an average star became a living, thriving oasis in the cosmic dark. Yet the very precision of our measurements has unveiled a new layer of the mystery, forcing us to ask an even deeper question. Is the strength of dark energy truly constant, as Einstein's cosmological constant suggests, or is it something that changes over time? This is not a minor technicality. It's a fundamental inquiry into the engine of the cosmos that could completely rewrite the final chapter of the universe. The standard model of cosmology, known as lambda CDM, is built on the assumption that dark energy is static, that the lambda, the cosmological constant, is indeed constant. Its repulsive power remains unchanging, a fixed property of the vacuum of space itself. This model has been stunningly successful at fitting a vast array of data, from the cosmic microwave background to the large-scale structure of galaxies. But what if that success is masking a more dynamic and evolving reality? This possibility has given rise to a compelling alternative known as quintessence. In ancient philosophy, quintessence was the fifth element, the pure and perfect substance that filled the heavens. In modern cosmology, it represents a radically different vision of dark energy. Instead of a static energy inherent to empty space, quintessence proposes that dark energy is a dynamic field, a kind of cosmic fluid that permeates all of space, but whose energy density can slowly dilute or increase over billions of years. Imagine it not as a fixed feature of the cosmos, but as something that has a history and an evolution, much like the universe itself. This field would be reminiscent of the Higgs field or the inflaton field that powered the Big Bang's rapid expansion, but it would be acting in the present epoch, its subtle changes dictating the acceleration of the universe. The critical difference between a static lambda and a dynamic quintessence field is captured in its equation of state, the value W. For a true cosmological constant, W is locked at exactly -1. But for quintessence, W could be slightly greater than -1, meaning its repulsive power could be slowly weakening over time. The implications of this distinction are nothing short of cosmic. If dark energy is a form of quintessence that is slowly fading, the current acceleration of the universe might eventually weaken. Gravity, given enough time, could once again become the dominant force on the largest scales, potentially leading to a future that is very different from the cold, isolated Big Freeze. Conversely, if the field evolves in the other direction, with W becoming less than -1, we could be facing a far more violent end. This phantom dark energy scenario would mean the energy density of dark energy actually increases as the universe expands, leading to an exponentially accelerating rip that could tear apart galaxies, solar systems, and eventually the very fabric of spacetime itself in a cataclysm known as the Big Rip. Determining whether W is exactly -1 or deviates from it by even a tiny amount is therefore one of the most important goals in all of science. Detecting such an subtle evolution, however, is a monumental challenge. We are trying to measure a potential change in the strength of a force across billions of years of cosmic history. It requires mapping the expansion rate of the universe with unprecedented precision at different epochs, comparing the ancient past to the more recent past and the present day. This is where a new generation of astronomical observatories comes into play, instruments designed not just to see deeper into space, but to take a detailed medical history of the cosmos. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, or LSST, is poised to be a game-changer in this endeavor. From its perch in Chile, this revolutionary telescope will undertake an unprecedented 10-year survey of the southern sky, capturing the entire visible sky every few nights. It won't just take a static picture, it will create a colossal cosmic movie, monitoring the brightness of billions of galaxies and discovering millions of new supernovae. The sheer volume of data from the LSST will allow astronomers to construct a vastly more detailed map of the cosmic distance ladder. By tracking thousands of Type Ia supernova at different distances and therefore different look-back times, scientists can measure the expansion rate with finer granularity than ever before, searching for any slight deviation from the predictions of a pure cosmological constant model. Furthermore, the survey will map the positions of billions of galaxies, allowing for an exquisitely precise measurement of the Barrian acoustic oscillation scale at multiple points in cosmic history. Seeing how this standard ruler has been stretched over time provides a completely independent and highly robust measurement of the universe's expansion history. By combining these two powerful methods, the LSST and other future missions like the Nancy Grace Roman Space Telescope will shrink the error bars on the equation of state W to a razor's edge. They will not simply be looking to confirm the standard model, they will be actively hunting for a crack in it. The discovery that W is not exactly -1 would be a paradigm-shifting event, forcing us to replace the simple cosmological constant with a rich new physics of a dynamic dark energy field, finally opening a direct window into the evolving force that controls the destiny of all we see. While we scan the skies and probe the deep underground for any sign of dark matter, some of the most tantalizing hints haven't come from a definitive discovery, but from strange, unexplained signals that simply refuse to go away. These are the astronomical anomalies, mysterious glows, and unexpected spikes of energy that don't quite fit our understanding of conventional astrophysics. They are the cosmic whispers that could, just maybe, be the first faint voices of dark matter particles finally announcing their presence. Among these, two signals have generated more excitement and debate than any others, each representing a different strategy in the hunt for the invisible. The first of these enigmatic signals comes from the very heart of our own galaxy, a turbulent and crowded place that should be, ironically, one of the most promising places to look for dark matter annihilation. As we discussed, the center of the Milky Way is predicted to have an incredibly high density of dark matter, and if particles are colliding and annihilating anywhere, the rate should be highest there. For over a decade, scientists analyzing data from the Fermi Gamma Ray Space Telescope have been studying this region, and they've found something peculiar: a significant and persistent excess of gamma-ray photons with energies around a few gigaelectronvolts or GeV. This glow, known as the galactic center GeV excess, forms a smooth, diffuse halo around the core of the galaxy, and its properties are surprisingly consistent with what we might expect from the annihilation of hypothetical dark matter particles called WIMP with a mass in the tens of GeV range. The signal seemed to have the right shape, the right symmetry, and the right energy to be the smoking gun everyone had been waiting for. However, the galaxy's center is a notoriously messy environment, packed with other potential sources that could mimic this signal. The primary alternative explanation is a population of thousands of previously undetected millisecond pulsars, the incredibly dense, rapidly spinning corpses of dead stars that beam out powerful jets of radiation, including gamma rays. If there is a large, faint population of these objects too distant to be seen individually, their combined emission could easily create a smooth, excess glow that looks just like a dark matter signal. For years, the debate has raged. Proponents of the dark matter interpretation point to the signal's specific characteristics, arguing that its distribution and spectrum are a better fit for annihilation than for any known astrophysical source. Skeptics counter with increasingly sophisticated models showing that the stellar population in the galactic center could indeed produce the requisite number of pulsars. To this day, the Fermi-LHT collaboration itself has not claimed a discovery, and the true nature of the GV excess remains one of the most heated and fascinating debates in astrophysics, a perfect example of the immense challenge in separating a potential dark matter whisper from the cosmic cacophony. The second major anomaly is a ghostly line in the X-ray sky, a story that begins not with a broad excess, but with a startlingly specific spike of energy. When astronomers pointed X-ray telescopes at massive, dark matter-rich objects like the Perseus galaxy cluster, they noticed something no one was expecting: a faint but consistent emission line at an energy of 3.5 kiloelectronvolts or 3.5 keV. This was not a broad smear of energy, it was a sharp spectral line, the kind of signature that typically points to a specific atomic transition or a very specific physical process. The problem was, there was no known atomic element or known astrophysical process that could produce an X-ray line at this precise energy. It was a complete mystery. This is where dark matter theorists saw an opportunity. What if this line wasn't from ordinary matter at all? One compelling hypothesis suggests it could be the signature of a sterile neutrino, a hypothetical, heavier cousin to the standard neutrinos we know, and a prime dark matter candidate. If these sterile neutrinos exist, they would be unstable with a very long but finite lifetime. Every so often one would decay, and in that rare moment of decay, it would produce a standard neutrino and a photon with an energy directly tied to the mass of the parent particle. For a sterile neutrino with a mass of 7 keV, that decay photon would be an X-ray with an energy of exactly 3.5 keV. It was an incredibly elegant explanation. The precise energy of the line would directly reveal the mass of the dark matter particle itself. The signal was detected not just in one cluster, but in stacks of many clusters and even in the Andromeda galaxy, strengthening the case that it was a universal phenomenon linked to dark matter halos. Yet, like the GV excess, the 3.5 keV line has faced intense scrutiny. Other groups analyzing data from different X-ray telescopes, like XMM Newton and Chandra, have reported non-detections, failing to see the line in places where it should be. Critics argue that the signal could be a complex artifact of the instruments themselves, or the result of multiple overlapping emission lines from common elements like potassium and chlorine in the hot plasma of galaxy clusters, which could combine to create a false line at the wrong energy. The controversy highlights the extreme difficulty of this work, where scientists are often working at the very edge of their instrument sensitivity, trying to distinguish a potentially universe-altering signal from a subtle systematic error or a mundane astrophysical blend. The fate of the 3.5 keV line remains unresolved, a spectral ghost that continues to haunt the edges of our data, refusing to be fully confirmed or dismissed. These controversial signals represent a critical phase in the scientific process. They are not failures, but rather the necessary growing pains of a field probing the absolute limits of detection. Each anomaly forces both theorists and observers to sharpen their tools, to build better models of astrophysical backgrounds, and to design more sensitive future experiments that can finally provide a definitive answer. They are the mysterious clues in our cosmic detective story, the cryptic messages that could either lead us to the identity of the universe's missing matter or teach us something entirely new and unexpected about the complex astrophysics of the universe we thought we knew. But if the cosmological constant and quintessence represent our best attempts to work within the known framework of physics, A far more radical school of thought questions the entire premise. What if we are inventing a mysterious dark energy to explain the accelerating universe because we've been using the wrong rulebook for gravity all along? This is the bold proposition of modified gravity theories, which suggest that Einstein's theory of general relativity, while spectacularly successful in our solar system and with neutron stars, might break down on the very largest cosmic scales. Instead of invoking a new, invisible energy component, these theories propose that we simply need to tweak the laws of gravity themselves to account for the observed acceleration. One of the most sophisticated and well-developed frameworks in this category is known as F of R gravity. In Einstein's equations, the left-hand side that describes the geometry of spacetime is exquisitely balanced against the right-hand side that contains all the matter and energy. The R in F of R stands for the Ricci scalar, a mathematical quantity that describes the curvature of spacetime. In standard general relativity, this term is linear. F of R gravity proposes that this relationship is not so simple. It suggests that gravity behaves differently in regions of extremely low curvature, like the vast, near-empty voids between galaxies. By adding a specific mathematical function to the curvature term, these theories can produce a repulsive effect that mimics dark energy, causing the universe to accelerate without needing any mysterious substance. The appeal is profound. It returns us to a seemingly simpler universe, one where the acceleration is a feature of spacetime's geometry rather than evidence of a missing 95% of the cosmos. The challenge, however, is that these theories must pass a series of rigorous cosmological exams, and they often struggle to match the full suite of observational data that the standard lambda CDM model explains with such precision. The most powerful test comes from the growth of structure. In a universe dominated by a cosmological constant, the accelerated expansion begins relatively recently, allowing gravity plenty of time to pull dark matter into the elaborate cosmic web we observe. In many modified gravity models, the effective repulsive force also affects how quickly matter clumps together. The predictions for the growth of galaxy clusters and the subtle weak lensing of light by large-scale structures often deviate from what is actually measured. The bullet cluster remains a particularly difficult hurdle. Its clear separation of the dominant mass from the visible matter is a natural outcome for collisionless dark matter, but is extremely challenging for most modified gravity theories to explain, as the gravity should remain tied to the location of the visible mass. This constant tension with data forces the proponents of modified gravity to make their theories increasingly complex, adding mechanisms to screen the modified behavior in regions of high gravity, like our solar system, to avoid contradicting the exquisitely precise tests passed by general relativity close to home. This screening ensures that planets orbit the Sun exactly as Newton and Einstein predicted, while only allowing the modified behavior to manifest in the low-density emptiness of intergalactic space. While this makes the theories more viable, it also diminishes their initial elegance. The scientific process is therefore playing out in a fascinating way. Cosmological observations are continually used to test and constrain these alternative models, not to dismiss them outright but to force them to evolve. The goal is not a battle between ideologies, but a rigorous search for the simplest and most accurate description of the universe. Whether the final answer is an elusive dark energy or a modification to our most fundamental understanding of gravity, the journey to find it is pushing the boundaries of human knowledge to its very limits. But this incredible precision in our measurements of the cosmos reveals an even deeper layer to the mystery, one that is perhaps the most profoundly puzzling of all. It's a question not about what dark matter and dark energy are, but about when we are. We find ourselves living in a remarkably special moment in the entire 14 billion-year history of the universe, a fleeting era where the densities of these two dark components are almost exactly comparable. Think about that for a moment. The density of dark matter, which controls the growth of structure, and the density of dark energy, which controls the expansion of space, are within a mere factor of 10 of each other right now. This is not a permanent state of affairs. It is a cosmic coincidence of breathtakingly perfect timing. For the vast majority of the universe's past, dark matter was overwhelmingly dominant. In the far, far future, dark energy will completely dominate, its influence growing as the universe expands and dilutes everything else. The window where the two are even remotely close is astonishingly narrow. To have both exist in such a delicate balance at the exact same time we are here to observe it feels less like a lucky break and more like a question the universe is demanding we answer. This is the essence of the cosmic coincidence problem. It forces us to confront an uncomfortable possibility that the fundamental constants of our universe might not be so constant after all, or that their values are strangely fine-tuned for our existence. Let's walk through the timeline to understand just how special this moment is. For billions of years after the Big Bang, the universe was a much denser place. Dark matter, whose density decreases simply as the volume of space increases, was the undisputed king. Its gravitational pull was the main driver of cosmic evolution, tirelessly working to pull matter together into galaxies and clusters. Dark energy, if it is indeed a property of the vacuum of space, would have had a constant energy density. But in that young, dense universe, its repulsive effect was utterly negligible, completely drowned out by the powerful gravitational pull of all that matter. The universe's expansion was steadily slowing down, just as everyone expected. Now, fast forward to the far future. The universe will continue to expand, and the density of matter, both dark and ordinary, will continue to drop. But the energy density of a cosmological constant would remain the same. Billions of years from now, the matter density will have plummeted to insignificance, while the dark energy density will hold steady. The universe will then be completely dominated by this repulsive force, leading to the accelerated expansion and the eventual isolation of the Big Freeze. The era of structure formation will be long over. The epoch of stars and galaxies will have passed. The cosmos will become a dark, empty, and ever-accelerating void. This makes our present era a breathtakingly brief crossing point between these two vastly different regimes. The fact that we find ourselves living at the precise moment when the two energy densities are crossing paths seems incredibly fortuitous. It's as if we woke up exactly at the stroke of midnight on the cosmic clock. The sheer unlikelihood of this has led some scientists to propose that it might not be a coincidence at all. Perhaps there is a deeper, physical connection between dark matter and dark energy that we have not yet discovered. Maybe they are not two separate, independent entities, but different manifestations of a single underlying substance. Theories have been proposed where dark energy evolves over time and its strength is somehow coupled to the density of dark matter. In these models, the so-called coincidence is actually a natural outcome of the physics, a dynamic equilibrium that maintains this balance for a significant period. This would elegantly solve the problem, but so far, no such theory has gained widespread acceptance or found conclusive observational support. The other, more philosophical resolution is to invoke the anthropic principle once again. In this view, the value of the dark energy density isn't a fundamental mystery to be solved by a unique equation. It is an environmental variable. We find ourselves in a universe where the dark energy density is small enough to allow galaxies to form over billions of years, yet present enough to cause the acceleration we now observe. In universes with a much larger cosmological constant, the repulsive force would have kicked in immediately after the Big Bang, ripping apart any potential for planets or life before it could even begin. In universes with no dark energy at all, the fate might be a big crunch, also cutting short any chance for long-term evolution. Therefore, the fact that we observe this specific balance isn't a bizarre accident we need to explain away with new physics. It is a prerequisite for our own existence. We could not possibly observe a universe that was not structured in a way that allowed for observers. This perspective can be deeply unsatisfying for physicists seeking a deterministic cause, but it remains a powerful logical argument that is incredibly difficult to dismiss. The cosmic coincidence problem, therefore, sits at a fascinating crossroads between physics and philosophy. It challenges us to determine whether the apparent fine-tuning of our era is a profound clue pointing toward a revolutionary connection between the two great dark mysteries, or whether it is simply a reflection of our own place in a vast and possibly multiverse. Resolving it will require more than just better data. It will demand a fundamental leap in our understanding of why the constants of nature have the values they do, and whether those values could ever have been different. So far, we've treated dark matter as a single, monolithic entity, a mysterious substance defined by what it does rather than what it is. But to truly understand its role as the architect of the cosmos, we need to probe its fundamental properties, and one of the most critical questions is a surprisingly simple one: how fast does it move? This isn't about the speed of individual particles zipping through a detector, but about their average velocity in the early universe, a property that cosmologists describe using the terms cold, warm, or hot. This distinction, which might sound like a minor technicality, is actually one of the most important factors determining what kind of universe we ended up with, and it lies at the heart of both the grand successes and the lingering puzzles of our cosmic model. To grasp why temperature matters so much, we need to think about gravity's greatest adversary, motion. In the early universe, gravity was trying to pull those tiny density fluctuations in the dark matter into ever denser clumps. But if the dark matter particles were moving too quickly, they would possess enough kinetic energy to simply stream out of these nascent gravitational wells, effectively washing out the small-scale ripples before they could grow. Imagine trying to gather a swarm of hyperactive bees into a single hive versus herding a flock of slow-moving sheep. The bees' high speed would make it nearly impossible to contain them. This is the core idea behind the hot dark matter hypothesis. In this scenario, dark matter would consist of very light particles that move at speeds close to the speed of light, making them hot. The problem is, this high velocity would smooth out all the small-scale fluctuations. Gravity would only be able to start pulling things together on the very largest scales first, creating a top-down scenario where enormous superclusters would form first and then fragment into galaxies. This model was decisively ruled out by observations. We see small, dwarf galaxies that are incredibly ancient, proving that structure formed from the bottom up, with small objects merging to form larger ones. The universe we see is simply too lumpy on small scales for hot dark matter to be the primary ingredient. The overwhelming success of our current model is built upon the foundation of cold dark matter. The cold here means that after the Big Bang, these hypothetical particles were moving relatively slowly compared to the speed of light, their thermal velocity dampened by their potentially significant mass. This lethargy was their greatest strength. Because they were slow-moving, they were easily captured by even the faintest gravitational tugs of those initial density fluctuations. They couldn't escape, so they clumped together efficiently and hierarchically, first forming tiny halos that then merged to build larger and larger structures. This bottom-up process perfectly explains the universe we observe, the intricate cosmic web, the existence of faint dwarf galaxies in the early universe, and the precise pattern of the cosmic microwave background. The evidence for cold dark matter is etched across the sky on the largest scales, and it forms the C in the lambda CDM model, the incredibly successful standard model of cosmology. Yet, for all its grand-scale triumphs, the cold dark matter paradigm has faced persistent challenges on smaller galactic scales, the very cuspous, core, and too big to fail problems we discussed earlier. The simulations predict an abundance of small, dense dark matter subhalos and centrally concentrated cusps, while observations of real dwarf galaxies suggest flatter cores and a scarcity of the most massive satellites. This tension has led some physicists to ask if a slight modification could solve these issues without undermining the model's large-scale success. Could dark matter be just a little bit warm? Warm dark matter represents a middle ground. It would consist of particles that are lighter than those in the cold scenario, giving them a higher thermal velocity, not enough to erase small-scale structure entirely like hot dark matter, but just enough to potentially suppress the formation of the very smallest and densest clumps. This slight warmth would prevent dark matter from collapsing into extremely sharp central cusps, potentially naturally creating the flatter cores we infer from observations. It would also reduce the number of tiny satellite galaxies predicted to orbit large galaxies like the Milky Way, potentially bringing the theory into better alignment with the number we actually see. The most popular candidate for warm dark matter is the sterile neutrino we touched on earlier. Its lightness and lack of interactions would give it the necessary higher velocity to smooth out the smallest scales. However, warm dark matter is a delicate balancing act. If the particles are too warm, they would suppress the formation of all small galaxies, including the faint but real dwarf spheroidals we do observe orbiting our galaxy. The constraints from counting these ancient dwarf galaxies and from studying the Lyman alpha forest, the intricate absorption lines in the light of distant quasars caused by clouds of intergalactic hydrogen, place very tight limits on just how warm dark matter can be. These observations tell us that any thermal velocity must be very small. It can't suppress structure on scales larger than about a typical dwarf galaxy. So while warm dark matter remains a fascinating possibility for addressing the small-scale puzzles, the window for it to work is extremely narrow. The evidence still overwhelmingly points to a dark matter particle that is predominantly cold, leaving us to solve the small-scale anomalies through other means, like the complex effects of baryonic feedback or a very subtle level of self-interaction. The temperature of dark matter, therefore, is not just an academic label. It is the key that unlocked the large-scale structure of our universe, and its precise value continues to guide our search for the identity of the cosmos's hidden architect. And this brings us to the final, and perhaps most profound, mystery of all, a question that goes beyond what dark energy is and asks what its existence means for our most fundamental understanding of reality. For centuries, we've operated under the assumption that space and time are the immutable stage upon which the drama of the universe plays out. But dark energy challenges this at the deepest level, forcing us to ask, could space-time itself not be fundamental? What if the stage is an illusion and the acceleration we see is a clue to a deeper, more bizarre truth hiding in the quantum code of the cosmos? One of the most radical ideas emerging from this line of thinking is the holographic principle. It proposes that our perception of a three-dimensional universe, complete with the seemingly empty void of space, might actually be a projection from a two-dimensional surface encoded at its boundary, like a cosmic mirage. In this view, all the information contained within a volume of space is actually stored on its surface, much like the information on a hologram is encoded on a two-dimensional film. This isn't just a metaphor, it's a serious mathematical framework that has emerged from studies of black hole thermodynamics and string theory. If true, it means the universe we experience is a kind of illusion, and the true fundamental reality is played out on a distant, lower-dimensional surface. So where does dark energy fit in? In a holographic universe, the acceleration we attribute to dark energy might not be caused by a substance or a field within space, but could instead be a consequence of how information is encoded and processed on that fundamental boundary. The vacuum energy which causes the repulsion might be linked to the number of fundamental degrees of freedom available in the underlying quantum description. The incredible smallness of the observed dark energy density could then be a natural outcome of this cosmic data compression, a signature that we are indeed living inside a vast and complex hologram. Another breathtakingly different approach is the idea of emergent gravity, championed by physicists like Eric Verland. This theory turns everything we think we know on its head. Instead of gravity being a fundamental force described by Einstein's geometry of spacetime, Verland proposes that gravity, and by extension spacetime itself, is not fundamental at all. It might be an emergent phenomenon, a side effect of the behavior of microscopic quantum information. Think of it like the concept of temperature. Temperature isn't a fundamental property of a single atom. It's a collective, statistical property that emerges from the frantic motion of trillions of atoms. In the same way, Verland suggests that what we perceive as gravity emerges from the changes in the entropy, or the disorder, associated with the fundamental bits of information that make up the universe. In this framework, the observed acceleration of the universe isn't due to dark energy, but is a result of this emergent gravitational law behaving differently on the largest scales. The mysterious force pulling galaxies apart could be a testament to the fact that we've been misidentifying an entropic force for a fundamental one. The need for a dark energy component simply vanishes, replaced by a new understanding of how gravity naturally changes in an expanding universe filled with dark matter. These ideas are not just mathematical curiosities, they represent a profound paradigm shift in physics. They suggest that our quest to find a particle of dark matter or to pin down the exact equation of state for dark energy might be missing the point entirely. We might be like cartographers meticulously mapping every detail of a vast landscape, only to eventually discover that the map is not the territory, that the territory itself is a projection. The hauntingly perfect value of the cosmological constant, too small to be explained by quantum field theory yet too significant to ignore, could be the most important clue we have. It might be the universe's way of telling us that spacetime is not the foundation of reality, but a derivative concept that emerges from something far more strange and wonderful, a universe built not on forces and fields but on information. From the gravitational ghost that holds galaxies together to the repulsive force tearing the cosmos apart, these 30 mysteries are not merely gaps in our knowledge, they are the very frontier of fundamental physics. They remind us that the universe is far stranger and more wonderful than we ever imagined, with 95% of its content remaining completely invisible to us. We have mapped its effects with stunning precision, felt its gravitational pull on the largest scales, and seen its influence in the first light of creation, yet its true nature continues to elude us. This is not a story of failure, but one of exhilarating potential. It represents the most profound invitation to explore, a challenge that has united astronomers, particle physicists, and cosmologists in a grand collaborative effort to read the hidden language of the cosmos. This quest is accelerating. Next-generation instruments are coming online, each more powerful than the last. The Vera Rubin Observatory will scan the entire southern sky every few nights, creating a cosmic movie that may reveal subtle clues in the dance of galaxies. The Nancy Grace Roman Space Telescope will peer back in time to precisely measure the expansion history of the universe, tightening the constraints on dark energy. Deep underground, ever more sensitive detectors continue their patient watch for a faint recoil, while particle colliders like the LHC strive to create dark matter in the lab. In the silence of space, telescopes are listening for the faint whisper of an action or the telltale X-ray signature of a sterile neutrino. We are not just waiting for an answer, we are actively building the tools to force the universe to reveal its deepest secrets. This journey into the dark underscores a beautiful truth about science. It is a self-correcting, ever-evolving process. Every null result, every unexpected anomaly, And every stubborn tension, like the Hubble constant discrepancy, is not a roadblock but a signpost guiding us toward a more complete theory. The inability to find WIMP has opened the door to a wilder menagerie of candidates, from fuzzy dark matter to primordial black holes. The struggle to reconcile the early universe with the modern one hints that our understanding of gravity itself may be on the verge of a revolution. This is how knowledge expands, not in a straight line, but through a series of thoughtful questions, careful observations, and the relentless pursuit of a clearer picture. So, as we stand between a past we are only beginning to understand and a future we can scarcely predict, the most important thing we can do is nurture that sense of wonder. Stay curious, follow the progress of these incredible experiments, read about the latest discoveries and the enduring puzzles, share that awe with others. Consider supporting public funding for basic scientific research, which fuels this long-term exploration into the unknown. The greatest discoveries in human history have always begun with a simple question about the world around us. The mystery of dark matter and dark energy is that question for our time, a cosmic riddle that beckons us to look up at the vast, dark sky and not see emptiness, but a universe filled with possibility waiting to be unveiled.